Ah, tiene el adaptador, ¿verdad? Pero no me gusta tirar los cables mucho.
Uno, dos. Uno, dos, tres.
¿Aló? Hola. Hola, hola. Let's start. Yes. Bienvenidas y bienvenidos a KHIPU e benvindos ao KHIPU. My name is Jocelyn Dunstan. I'm the local chair of KHIPU 2025. After 2 in-person and 1 online versions held in Montevideo, this is the first KHIPU outside Uruguay, and having you all here is a real pleasure. KHIPU seeks to support the advancement of our immense regional talent to shape the future of artificial intelligence through groundbreaking research and a supportive ecosystem. Welcome. What makes this conference special? Bringing the best speakers with local and foreigner affiliations, keeping in mind diversity and inclusion. And this is really important, so we will have some slides about it. Also, the speakers cover their own expenses, and we fund the candidates that you are here. And the idea of funding candidates is really important, and is thanks to the support of our sponsors that are here, and also the partners of the conference. In terms of diversity and inclusion, I would like to invite Luciana Benotti, a professor at the Universidad Nacional de Córdoba, to talk more about that.
Well, hi everyone. Since the beginning in 2019, KHIPU has been committed to diversity and inclusion. We are continually striving to improve the principles in each edition. One of the key commitments is geographic diversity. Latin Americans, we are underrepresented in artificial intelligence events worldwide. And KHIPU is one of the few opportunities to participate in these kind of events as we are here today. So the map present here that KHIPU prioritize Latin American participation and strives to do it representing each of the countries in our continent. So here you see the nationality and the country of residence of the participants that have been selected, that have applied and have been through the selection process of KHIPU. Beyond geographic diversity, these graphs show our efforts to include students and also to improve the representation of underrepresented genders in not only in events like KHIPU in our region, but worldwide. So these are genders that are underrepresented worldwide in artificial intelligence. And you can see here our efforts to improve this. And also, this is the first year we have implemented family care grants, and we think that's also useful in order to improve gender diversity. This is why we organized it. And as Jocelyn also mentioned, socioeconomic diversity is also very important for KHIPU, and this is why so it's very important for us to find sponsors in order to fund the trips of anyone that needs funding to attend KHIPU. Finally, I'm thrilled to welcome you all to the largest KHIPU ever. In the next map, here you can see the representation not only of selected participants, but of all organizers, speakers, sponsors that will be joining this edition of KHIPU. And I wanted to mention explicitly all the countries that are represented. This is Argentina, Bolivia, Brazil, Chile, Colombia, Costa Rica, Cuba, Ecuador. You still hear me? No. Guatemala, Mexico. It's a bit high for me, I'm not so tall. So Guatemala, Mexico, Nicaragua, Peru, Uruguay. If you hear your country there, you are allowed to make some gesture. I will start again, yes. So Argentina, Bolivia, Brazil, Chile, Colombia, Costa Rica, Cuba, Ecuador, Guatemala, México, Nicaragua, Perú, Uruguay. And we also have non-Latin American countries, Australia, Austria, Canada, Denmark, France, Germany, Italy, Netherlands, Nigeria, Spain, Switzerland, United Arab Emirates, and United Kingdom and United States. And that's it.
And now we have some words from authorities. First of all, we are here in the beautiful facilities of the Faculty of Economics and Administration of the Pontificia Universidad Católica de Chile, and I would like to thank to its dean, Professor José Miguel Sánchez, for believing in this project from the first moment and give us some greetings, please.
Well, thank you very much, Jocelyn. It's a real pleasure for me to give you a very warm welcome this morning. It's a true honor to our university, the Pontificia Universidad Católica de Chile, and our Faculty of Economics and Administration to have you here and to host KHIPU 2025 Latin American Meeting in Artificial Intelligence, the most important artificial intelligence conference in Latin America, and to have it here in our facilities. This event is not just about cutting-edge research and innovation, it's about building a strong and collaborative artificial intelligence community that transcends borders. The presence of speakers and participants from across Latin America and the world makes this event a unique space for internationalization and an incredible opportunity for everyone, not only for those attending, but also for our own students who can benefit from exposure to a dynamic and rapidly evolving interdisciplinary field right here at our facilities. Artificial intelligence is reshaping the global landscape, and its role in economics and business is more crucial than ever. From decision-making and labor market challenges to automation and new business models, artificial intelligence is transforming the way we work, compete, think, teach, and innovate within organizations. As humans, it is our responsibility to harness this powerful tool to foster well-being and progress for everyone. We believe that we not only have the opportunity, but also the duty to explore artificial intelligence impact across industries, organizations, and society, working together to ensure its ethical and responsible use in all its capabilities. This conference is an opportunity not just to learn about the latest advancements in AI, but also to connect, to exchange ideas, and build lasting collaborations. And encourage you to make the most of these days, to enjoy your stay here, engage in the sessions, connect with peers, and take a moment to experience our faculty and enjoy our campus. I hope you have time to walk around the campus. It's very, very beautiful. I really recommend that. Welcome to the Facultad de Economía y Administración from our Pontificia Universidad Católica de Chile and to KHIPU 2025. I hope this experience inspires new ideas, fosters meaningful partnerships, and helps shape and share vision of the possibilities of the future of artificial intelligence in our region and beyond. Thank you very much and very welcome.
Thank you very much. In representation of the Pontificia Universidad Católica de Chile, I invite the President for Research, Professor Pedro Buchón.
Good morning. First, I would like to extend my gratitude to the authorities present today, Jose Miguel Sanchez, Dean of the Faculty of Economics and Administration at UC Chile, and Jocelyn Dunstan, local chair of KHIPU, researcher at the Millennium Institute for Foundational Research on Data, and academic at the UC Chile School of Engineering. And certainly all the organizers of KHIPU, and of course all the attendees of this meeting. Mainly I can see, many early career researchers or to be, so it's good to be giving you some words today. I would like to begin by thanking the Millennium Institute for Foundational Research on Data for the invitation to deliver these welcoming words at KHIPU, an event that unites the most prominent academic community in the field of artificial intelligence in Latin America. UC Chile is honored to hold this Millennium Institute and other centers that strongly collaborate with both Chilean and international university, which stands as a benchmark in Latin America. In this case, leading the way in cutting-edge and multidisciplinary research. The researchers that integrate the institutes and the centers possess the ability to understand the complexity on data, extract its value, and transform it into benefits for society. In a world where AI is advancing rapidly, their work is more important than ever. Returning to KHIPU, today we inaugurate the sixth edition here at the Faculty of Economics and Administration of our university. As far as I know, this is the first time this event is being held outside of Uruguay. So on behalf of UC Chile, it's an honor to welcome you to our institution, which proudly carries out 136 years of history. It is with great excitement that I welcome you to this year's conference, where we gather to explore the transformative potential of artificial intelligence. AI holds the promise of significantly enhancing lives and boosting business prosperity. However, solving a challenge as complex as this one requires diverse perspectives and the brightest minds for every corner of the globe. This conference aims to empower Latin American talent, research, and enterprises in AI by providing advancing training in machine learning topics, such as deep learning and reinforcement learning. Moreover, it seeks to strengthen the regional AI community by fostering collaborations and facilitating knowledge exchange with the global research network. And additionally, it is desired to raise awareness about the positive impact AI can have on the future of Latin America, where students play a pivotal role. The mission of KHIPU is to advance Latin American talent, research, and companies shaping the future of AI through innovative research and supportive ecosystem. And that is why, as a university and as Vice President for Research of this university, we feel deeply honored to host this meeting and contribute to the realization of this new edition. I would like to highlight some metrics of interest which go a little bit beyond what was just referred to, like in general terms. As far as I know as well, we have here 300 participants from across different sides of the world, mainly Latin America, which were selected from 900 applicants. It is also worth recognizing that KHIPU actively promotes, as you just heard, gender equity and the representation of diverse cultures, disciplines, and regions throughout Latin America, which is a very strong asset, and I really appreciate that it has been highlighted during this inaugural session. There's no denying that artificial intelligence has become a fundamental component of modern life, transforming every aspect of our daily routines, including academic work and education, as the Dean has just highlighted. For us as a university, this presents a multitude of challenges and certainly many and vast opportunities, especially given the rapid pace at which AI is advancing. Despite this rapid progress, human participation and the responsible use of AI remain essential. These principles form a core part of the values that attendees will engage with at this conference, just as they do for our undergraduate and graduate students here at UC Chile. As a university, we greatly appreciate the organization of an event that addresses artificial intelligence in all its dimensions. And we also wish you to acknowledge the hard work of the organizers and everyone who has contributed to making this event possible here in Chile. May this be a fruitful week of knowledge exchange meaningful debate, lectures, and strong collaboration. Thank you very much.
So I would like to thank the board that makes this possible, the academics in the committees, the Dean of Engineering, Professora Loreto Valenzuela, who believes a lot in this event. I also want to formally thank our sponsors who have the conviction of the relevance to this conference for Latin America. And now I declare open KHIPU 2025. So, KHIPU is happening every 2 years, and what happens in between these 2 years is KHIPU X. The idea of KHIPU X is to, inspired by Indaba X, that is happening in Africa, is to have some events to keep the spirit alive of the community. So there were 26 applications for funding this type of events, and there were 9 events funded from 7 different countries. So the idea is to, that the KHIPU X is 1 to 3 days events, and those are is the map where they were funded. So these are some of the topics that they were funded, and some photos of those events. So what is the take-off message? Keep following KHIPU's networks and social media, because in that way you could maybe in the future bring KHIPU to your own university or center. And now I will briefly talk about what's going on from now on in KHIPU. So Monday, we have the lecture of Jorge Perez after this moment, who is sitting there. Then we have a coffee break. And in general, today is about foundations. Like, it might sound a bit basic, but we need to be all of us in the same page. So today is about machine learning and deep learning fundamentals. It's about an introduction to natural language processing, and we have the practicals in the afternoon. We also have a formal event or social event that is to make your own KHIPU. So if you don't know why this conference is called KHIPU, by the afternoon you will know for sure what is all about the KHIPUs. On Tuesday, the idea is that Monday, Tuesday, Wednesday is a school, and the school has this structure. We have lectures, spotlight talks that are 15-minute talks from different researchers from Latin America. Then we have the lunch, when we have poster sessions. So if we enter the faculty and you saw like panels for posters, it's because during lunchtime, the idea is that you see those posters. And then we have some coffee breaks, we have sponsored talks, we have research talks in the afternoon, and then every Monday, Tuesday, Wednesday, we have the practicals. So Wednesday is, as I said, in that structure, and Thursday is different. On Thursday, we have several parallel sessions on, for example, cybersecurity, NLP, economics, navigating the challenges of real-world applications, reinforcement, strategic artificial intelligence, human rights, computer vision, and economic perspective on artificial intelligence. So then you will have to choose what room you want to go, and there will be those parallel sessions, and then we will have 2 panels in the afternoon. So no practicals on Thursday, and no posters on Thursday. And finally, Friday is not here, it's in the city center in Seina, which is close to the Metro Universidad de Chile, and we will start at 10 a.m., notice that, a bit later, for the Women in Artificial Intelligence event, and then we have the closing event with all the speakers that from Domingo Meri to René Vidal. And then we have a party to finish up KHIPU. So that's what will be happening during the week. We are all okay with that? Yeah? Okay. So being 9 a.m., 9:01, so very good. Very Latin American, being on time. I would like to introduce our first lecturer and my friend, Jorge Perez, who is the co-founder and chief product at KHIPU.AI, a Chilean company accelerated by Y Combinator and dedicated to healthcare coordination. Before co-founding Zero, he was a faculty member at the Computer Science Department of the University of Chile for over 10 years, and a researcher at the Millennium Institute for Foundational Research on Data. Let's welcome Jorge.
Ojalá. Pero ya estoy. Good. Thank you so much, Jocelyn. So my name is Jorge, and I will be giving the first, most basic lecture about the fundamentals of deep learning. A bit of a disclaimer, I am no longer a researcher, not an academic. I haven't given a talk in a lot of years. Mostly my day-to-day is just selling my product to some clients. So bear with me, yes? This is my first lecture in many years. So just to start with something, because artificial intelligence was not invented by OpenAI, it was and most of you are younger than me, so I wanted to start with a little bit of history. And so how do we get here where we are now in artificial intelligence? So maybe it's even before what I'm talking here, but around 1950, we have this information theory from Claude Shannon. If you don't know about information theory, you should go and read that paper, which is amazing. The guy invented the bit, which is, how can someone invent the bit? Yes, Claude Shannon invented the bit. He also talked about, he was interested in how much information a process has, and he invented a concept that is called entropy. What is important for us now is that he observed something very special. He said that after defining what information is, he observed that the spoken English language, but actually any language, has very little information. And how was defined? He defined this in this way. He said that if you have a sentence and you erase one of the words in the sentence, it's very easy to know what the words, what was the word that was missing. Yes, so you can complete the sentence. Yes, every one of us has this friend, and when you are talking to the friend, you're not complete sentence, and the friend complete your sentence at the end. Yes, it's kind of annoying. I am that friend to some people. This is not because they are magicians. It's because the language has little information, and this is what we are seeing now with this large language model. They are completing information, and they are sounding like intelligent. And then around the same time, in 1950, we have the Turing test. And most probably all of you know or have a notion of what the Turing test is. But just to give a brief, to what the test is, Turing was, at the time of the Turing test, the researchers were questioning themselves whether a machine can think. That was the question. Can a machine think? Yes. So it's similar to what we are discussing now. Yes. Is ChatGPT thinking? So Turing said that is a meaningless question. So he devised this test. When in the test there are three entities: two humans and one machine. So there is one human there is a wall, so the human cannot see the other two entities, and beside the wall, there is a machine and a human. And we say that the machine passed the test if after the human in this side of the wall interact with two entities, the human here cannot say which one was the machine and which one was the human. So that is the actual Turing test. So what Turing was saying is that it doesn't matter if the machine is thinking or not. It only matters if we think that the machine is behaving like a human. That is important from a psychological point of view. Yes, so Turing in that year, 1950, he predicted that in 50 years, we will have machines that pass the test. So he missed like for 10 years, but he was like very, very clear on what the innovation will be. Yes, at the same time, we have this strange word there, distributional hypothesis, and this is something in linguistics. So at the same time, the people in linguistics were thinking about the meaning of words. So the meaning of words was somehow related to, for them, to what people feel, to what people think about words. And there were some researchers that said that is also meaningless, and the meaning of a word is just a statistic property of the word. So the meaning of a word is just a summary of all the places in which this word can appear. And that is why the meaning of cat and dog, I would have to say perro and gato, cat and dog are similar, yes? Because they can appear in the same positions when we are talking, when we are writing, yes? And then around 60, it was 58, Rosenblatt invented the perceptron, and the perceptron was born. What is a perceptron? Is the most basic unit of an artificial neural network. And just to give you a sense of the hype of the perceptron, that year, the New York Times published this. They say that the perceptron is the embryo of an electronic computer that will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. That was published in a newspaper that year. You can go to the New York Times that year and you can see that. The perceptron was going to replace all the workers, yes? So similar to what we have now, yes? And around 50, the perceptron dies. Minsky and Paper, two researchers, they killed the perceptron. They didn't want to kill the perceptron. They were amazed about the perceptron, and they actually published a book that is called The Perceptron. But in the first, as every researcher, theoretical researcher, I used to be a theoretical researcher, in the first 10 pages, they describe all the things that the perceptron cannot do. Yes? The most simple thing that the perceptron cannot do, it was not able to simulate an XOR gate, which is a very, very basic gate of a computer. And the paper, after the 10 pages, the book has like 200 pages, but everyone read until the page 10, and then it killed the perceptron, and it started what we know now as the winter, artificial intelligence winter. It's not exactly that time, but you can think that around that time we had this winter. What is the meaning of a winter? Then we have a lot of hype, and then the technology didn't meet the expectations. It's not that the technology was bad, it's that the expectations were too high. The technology didn't meet the expectation, and then the funding goes to almost zero. And if you were a researcher around those years, I was not a researcher around those years, but working on artificial intelligence or perceptrons was kind of a taboo. Yes, you're working on some kind of esoteric thing. Yes. Luckily, people kept working on this. And then around this year, we have backpropagation and multi-layer perceptron, which is going to be the main topic of this lecture after the history. But we also have something important here. We have recurrent neural network that you will see during the lectures also. But we have the World Wide Web invented in 1990. And also, these two things, World Wide Web and GPUs, they are really, really important for what we are seeing now. The web all of us know the web, and in that time was an important thing. Now it's kind of part of our life. But the web is the thing that allowed us to have huge amounts of information. Without the web, we won't have that amount of information that we have now, yes? And in terms of GPU is, before GPUs, we were used in computer science to have a little number of processors that are very powerful. Each processor is very powerful, but we have a little number of them. And the GPU was a paradigm shift in which we have several thousand, maybe millions of processors. Each one of them is very simple, essentially doing summation and multiplications. And the people that invented GPU invented it especially for games, yes? And if you are old as me, you most probably play with an Atari, yes? And if you know, I've seen your children or some young people, what they are playing now, it's kind of a huge difference, yes? It's like sticks versus like real people, Fortnite and that stuff, yes? So GPUs were created for that, for gaming. And so we have, I just want to reflect a minute in which time we are now. We have huge amounts of data, and then this processor that is able to process that data like in parallel with many thousand millions of processors, very simple operations. So what happened next was in 2012, AlexNet came to life. What is AlexNet, or what is the summary of AlexNet? It's just, it's a very interesting network for processing images. But what's important about AlexNet is that it was the first example of a multi-layer perceptron, or similar to a multi-layer perceptron, that was implemented into a GPU. So we are using GPUs, huge amounts of data. Data in that kind was, in the case of AlexNet, were just images of animals and things. A lot of data, a lot of processing, the multi-layer perceptron, and the perceptron that was died until that point, it became alive again. And in that point, it's an inflection point, because all the huge enterprises like Google, Microsoft, they got interested in this again. They got interested in multi-layer perceptrons, in neural networks, GPUs, and then the thing exploded. We had Word2Vec that right now is kind of a prehistoric term, but it was a huge deal at that point. It was the first neural network that was able to process words, to have a meaning of a word in word embeddings, you call it now, yes, to like having a meaning of a word in a vector, but very efficiently. You can produce these meanings, these vectors very efficiently. And then you have attention, which is also really important. If you were around that year at the university and you were from Latin America, then you were very frustrated with Google Translate, because you put something there. I used to be a professor, and when I received a poorly written English in a paper, I said, okay, you used Google Translate, yes? And the student said, yes, I used Google Translate. So it was kind of a chain. And in a matter of a week, Google Translate went from garbage to extremely good. Some of this was because of attention, which is the main mechanism, and maybe the most important innovation in the last 10 years in artificial intelligence. I'm not covering attention in this talk, but most probably you will be seeing attention in the next lectures. And then you have transformers. That was a Google network that was invented to just use attention and almost nothing else. And from transformer, then around 2018, we have the first version of GPT, and also BERT, which was a big deal at that point. I don't know how many of you know what BERT is. Can you raise the hand? A lot of you. Okay, I was expecting a little bit less. So GPT and BERT, and then GPT-3, ChatGPT, GPT-4, and now Claude, Gemini, Llama, DeepSeek, and everything. And everything of this, all of this is based on the transformer. So the history is like way before ChatGPT, yes, just to be in the same page. So after the history, what we're going to be covering today is like we will talk about the basics, perceptron layers, activation functions, neural networks, then a very, I would say, an extremely high-level overview of how a neural network is trained, and then some more specific stuff like loss, derivatives, gradient descent, backpropagation, and some details and challenge during training. And if I have some time, I will talk about a little bit about my work now, which is not about research, but using this to solve real problems. So let's begin. So if you have any questions, you can just raise your hand, and maybe you can do the question also in Spanish. It will be okay. So this is a neuron, or at least that is what Wikipedia says. And, and this is a neuron, that small thing that we have in our brain. I'm not an expert on physiology, but in the Wikipedia page, it says that it received like electrochemic signals, and then it has a point of excitation, and then produce an electrochemical signal from here to connect to some other neurons. And there is something so simple that produces this kind of intelligent behavior in animals and in humans, then it's natural that the researchers wanted to kind of reproduce this in an electronic device, in a machine. Yes, so that is what Rosenblatt with the perceptron did, and some guys before him. So what is an artificial neuron? A perceptron is just, notice that it's kind of similar, even in shape, yes? So you have a very simple computing device which has inputs. Here's inputs are E1 to E5, and then an output. And every one of these like arrows going into this node has a special weight, which is just a real value that somehow represents the capacity of the dendrita. I don't know how to say dendrita in English. Dendrit, I don't know. The dendrita, which is this part of the neuron. Yes, yes. So the output is very simple. The most basic output of a perceptron is just a sum of every one of the weights of every dendrita multiplied by the input. Yes, just the sum. But if you want to represent this kind of excitation of the neuron, then you have to put some kind of function, which is called an activation function. We will be using this function. I will give you some other, but the idea is that you just apply the function over the sum of the multiplications. Yes, very, very simple. It's like kind of basic math. Yes, there is no NASA here. So what is the function that we will be using? Is that function that is extremely simple, which is the maximum between 0 and the input, and it's called the rectified linear unit. And using this function, what was the most important innovations in deep learning in the last 20 years, believe me. So before that, we can also use several other functions. And the main idea of the function is just, they are just trying to represent this idea of having input, and then at some point, the neuron is excited, and then give output as a result. So we will be using this one, but for a long time, this one was used. But now, for reasons of training and some other reasons like efficient implementation, we are going to be using this one. But in your mind, you can think that we can have any activation function, yes? And the math will work. So this is the function that we will be using. So just as an example, this is an artificial neuron, very simple. If we want to compute the output, we have 0, 1, 1, 0, 1 as the input. We do the multiplications, this cancels, so we only have like minus 1.4. This is Latin American notation. It should be a point here. Sorry. And it's going to be like a Spanglish talk. You already realized that, yes? So when you apply this, you have, when you sum this, you have 0.3, not comma 3, 0.3. You have the activation function, and the output is 0.3. Very easy. So another example, very similar, but now you have a different weights here. Notice that I didn't change the input, I just changed the weights, because that is what we are going to be changing. Change the weights of every one of the dendritas, and then we do the multiplication. This case is minus 1.1, and when you apply the activation functions, given that this number is less than 0, you just obtain 0. And we say that the perceptron is not activated. Very, very simple so far. No complications. So we also have, if you have been in a deep learning or a machine learning course, you notice that we are missing something that is a bias term, which is just another dendrit, another weight that you don't put inputs there. It's kind of it's called the bias term because you just kind of, if all the inputs are 0, anyway you shift the output, and you use it like there. But in this talk, just for simplicity, we will not be using bias terms. So bear with me, the more like theoretical researchers, that it's not big deal just for teaching purposes. So no bias term in this lecture. So what is an artificial neural network? It's just a network of these perceptrons in which the inputs of one of these perceptrons, the outputs of one of these perceptrons are the inputs of some other perceptrons in this kind of layer way. So we have the inputs here, we have the perceptrons here, so the inputs go to any one of these perceptrons, then the output of these perceptrons are going to pass as input of the other perceptrons. And each one of these arrows here has a weight, which is the capacity of the dendrita. And then finally, you have a final function. Notice that here we use an activation function. Here I use a different function, which is the output function that finally says what is the output of the network. So it's a very different way of computing if you are used to cycles, to iterations, to force, to while, and that kind of stuff. This is a different way of computing. It's just multiplication, summation, and then the output as input, some other layers, and then finally an output, which is a number. And we have to interpret that output if we want to solve a problem. So far, so good. So very good on time. So now I will give you a very, very extremely high-level overview how we train this stuff. So if you don't know anything about neural networks and you don't want to learn much more about neural networks, these are the slides for you. Later we will have like more specific. So assume that we have this kind of network, kind of huge network, but it's not huge for our like practical terms, but it fit the slide. And notice that we have 4 neurons at the end, and we have labels on them. The first said gato, perro, caballo, and pájaro, which is, I assume that you can read that. Yes? Cat, dog, horse, and bird. So we are going to interpret this network as if we give input, and then the output's going to be numbers at the end, and the biggest number is the one that we will consider as the output of the network. So if the biggest number is the first neuron, then we will say that the neuron is saying that the output is gato, and if the biggest number is the last network here, then we will say that the output of the network is bird, pájaro. So in the input, we will put an image, very nice image of a little cat, little gato. And how do we get an image into a neural network, the one that we are showing you here? You can just think that every one of these pixels, every one of the pixels in the image is just a number. So I will put every one of these pixels as an input of every one of the neurons of the first layer, yes, of the input layer. If you have worked with images, you know that every pixel is not just one number, but 3 numbers. But bear with me here for the example. Yes. So the gato transform in these colors here. The darker the color, the bigger the number. that is the example. The lighter the color, the lower the number. So we have just numbers here, real number. And then remember that all of these connections has weights, so we can do the multiplications and the summation, and then we can produce inputs to the next layer. And the next layer we have numbers also, and then the next layer we'll have numbers, and then the final layer will have numbers. And if we interpret this as we wanted to interpret this, the network is saying that the image is a caballo, horse, which is not a caballo, yes? It's a cat. So we are kind of angry with the network, and we say to the network during algorithms, please don't tell me caballo when I show you this image, yes? Because the answer is gato. So please, network, adapt your weights in a way that if you see this image again, you will say gato. So you notice that the weights were adapted, yes? So you put the gato again, you activate the neurons, and this time it says gato, and you are very happy, yes? What happened is you put a perro now, a dog, most probably the network will say gato again, and we repeat this. We say, no, this is not a gato, it's a perro, please adapt your weights, and then you adapt the weight, and then we just show the perro, and it will say perro, and we will be very happy. And if you show the gato, and everything worked, and you are lucky, then it will say gato and not perro, yeah? Go. And we can repeat this. So we put a caballo here, horse, it says perro, we are angry, then adapt your weights to say caballo, to say horse, and then a bird, it says perro, then you adapt to say bird, and then a gato again, and then a perro, and then a caballo, and then a pájaro, and then we repeat this 1,000,000 times, yes? 1 billion times. So what we have is in this extremely high level way of seeing the training of neural networks, you have an initial network, kind of a random network, a brain with no knowledge. We do this training, and then we obtain a trained neural network. What is the promise of this is that if you show the network, you put a new image that was not seen during the training, it was not one of the examples, the network will be able to respond correctly. In this case, gato, and in this case, perro, and if we are lucky enough, we can put an image like this, and it will say gato and caballo, yes, cat and horse. So we say that the neural network learned to recognize animals. So the question, like the philosophical question, is the network knows what an animal is? Maybe, I don't know. This is a philosophical question or psychological question. The important thing is that the network is working for our application. So that was the extremely high level definition of this, and now we are going to each one of the details to know exactly how you are training this neural network. So how does this actually work? And we are going now to the most boring part, loss, derivatives, and gradient descent. I will try to make it as joyful as possible. So this was our network. If we can try to formalize this a little bit, we can put a name to this input, a very boring name, x1. And this input has a label, yes, label 1. And we can transform this label into a target output, yes. We wanted this network to have the maximum number in the first neuron over there, and 0 on other. And we can also have the output of the network. Here the output is just numbers, but you can see that the maximum is not in the position that it has to be. So in order to implement this, if you remember my previous examples, we were like angry with this answer of the network. So in order to implement this angriness, we use an error function. An error function is just a way to measure how apart is the output of the network from the output that we wanted to obtain. Yes? And for now, we will just think that every error function will work. At the end of the talk, I will show you what the error function is there. If you know a little bit of this, you know what the error function is. But for now, for simplicity, just an error. And we have another example here, another target, another output of the network, and another error value for this other example. In practice, we have several of them. So we have a lot of target values, a lot of outputs from the network. The outputs are going to be the y sub I. The inputs are going to be the x sub y. And we have an error for each one of these pairs of training examples, x, y, and the error is the error of y sub I with respect to target sub I. We want to the average of this. So we have our training examples, we have our network that is in the process of being trained, and we can compute an average of all the errors that my network is having over all the data. This is called a loss or a cost or whatever, yes? But it's something that somehow summarizes how bad or good, if you're positive, is my network right now. So what we actually want to do is we want to minimize this expression. Yes, so we want to minimize the total average error that the network is doing over all my training examples. And one observation that is very important here is that given a fixed training data, so we have fixed data here, the loss, the error, the average error, is just a function of all the weights of the neural network, or all the parameters, if you're a statistician, yes? So this expression here is actually a function of the weights of the network. So what does it mean is that if we change a little bit one weight, then we will impact this error. So we have the loss here, the total average error, and we have the data here. And what we actually want to answer is what is the impact of changing one weight in the loss? So how does an increase or decrease in that way affect the loss? But we not only have one weight, yes, we have some other weights. Yes. We also want to know what is the impact of that weight on the loss, and also this other one. Yes, so what we want to do is to check how all these weights impacts in the average error of the. And we want to change the weights in a way that changing the weight minimizes the error. That is what we want to do. And when you study engineering, when you want to minimize a function, you have your tool of engineering stuff, and you try to do derivatives. Yes. So for now, let's think that all the weights are fixed except of one weight, just one of these. Just let's say that we are just looking at this weight. So if we are looking just at this weight and all the others are fixed, then we can kind of draw the loss function as a function of that weight only. It's like a one-dimension function. So assume that my current value of the weight is that one, and we want to put this value and to convert this value to this one, yes, which is the minimum of this function. So what we do here, we compute the derivative of the function, which is just the slope of the function, which is going in that way. And if the slope of the function is going in that way, we know that if we move in the other way, then we know. It's like we believe that if we move in the other way, then the function value is going to be less. So we compute the derivative of the loss with respect to the weight, which is that arrow there, and then we move in the way that is opposite to the derivative. And in that way, we have a new value. And then we repeat it again. Yes, so we compute the derivative again. It's in that direction, huge derivative, and we move in the other direction. We compute the derivative again, and we move it. At some point, the derivative can change the direction. In this case, the derivative is pointing to the other side, and we move into the other way, and then we go on with this. If we are lucky enough, we will reach the minimum point. But at least we have this hope that we are approaching to the minimum, and we are like walking in the direction of the minimum, at least walking in the direction that minimizes with respect to where we are now. So what we have here is a very simple update function. Yes, we have the current weight value, we have the derivative of the loss, the error, with respect to the weight evaluated in the current value. That was the arrow in the previous image. We also have this value here, which is how much we shall move, which is also known as learning rate, which is kind of a pretentious name for this value here that only says how much we will move. And this equation is saying that we want to move in the opposite direction of the derivative of the loss with a step that is proportional to this learning rate. And the new value is the amount of space that we move with respect to the current value. And this is called gradient descent. Yes? So many of you know what it is. If you didn't know, you know now. So this is the way in which we change the parameters of the network in a way that we change the parameter to minimize the loss, to minimize the error, the average error. So it's really, really simple. It's just an update, some values, a multiplication. The only complicated part here, kind of complicated, is this one. You may say, okay, this is just a derivative. Yes, we are like, I don't know, second year engineer student. We know we love to compute derivatives. But here, the derivatives is kind of special, yes, because we have we need the derivative of the loss of the error of the network with respect to any possible weight in the network. It could be millions, billions. Right now, we have billions of parameters, billions of weights in our current modern networks. So we have to compute the derivatives of a function that is a billion dimension. So it's you have a billion dimension function, and you want to derivate that function with respect to any one of these million variables. So it's not that easy, and you need some help here. So the question is, how do we efficiently compute this? And the algorithm to do this is called backpropagation. So backpropagation is essentially a way of computing derivatives. So it's kind of a pretentious name also for computing derivatives, but it's a clever way of computing derivatives in this context. So it's good to have that name. So before going to backpropagation, let me just formalize a little bit more how a network works. So here we have the inputs. The inputs now are x1 to x5. We have the neuron here, the perceptron, the activation functions, and the output that we are calling the output as h1 to h3. If we focus on the first neuron, just the first one, we can see the computation that the neuron is doing as applying the function to this sum of multiplications of inputs to weights. And this is going to be the output of the first neuron. And if you have done some linear algebra, you know that this is a dot product between two vectors. So you can interpret that as this one. Yes? So this is just a dot product between these two vectors. So if you compute this dot product, you will obtain exactly that sum and multiplication. Yes? Dot product, multiplication. Yes? Perfect. So I wanted to do this because it was a pain to do this animation. Yes. Okay. This was the most complicated animation of the presentation. Yeah. So if you look at the second neuron, then you have the same. Yes, and you can interpret that also as a dot product. And if you look at the third one, then you can also interpret that as a dot product. So if you have several dot products and you want to put all of them in a condensed way, then you can interpret everything as a matrix multiplication. So that's all. So it was very, very nice to have neurons, dendritas, activations, but at the end, it's just a matrix multiplication with a vector. So a very nice neural network layer is now this boring equation here, which is like a matrix of weights multiplied, like a matrix multiplication with a vector of inputs. Then you apply the activation function to each one of these positions, and then you obtain a vector as the output. This is like the modern way of looking at layers in neural networks. So if you want like a deep neural network, it's a network with a lot of layers, you have to repeat these operations only. So we will call H1 to this first layer, and then H2 is just similar equation with a second layer, a second matrix of weights, W2 here, which is multiplied by for the output of the previous layer, and then so on until a final layer, which is the multiplication of the final matrix of weights by this function, which is not an activation function, an output function, and then we obtain the last vector at the end. And here it is interesting that we have vectors here, but this can be a matrix with all the examples stacked. Yes? So the equation will work anyway if you put several examples in the same input vector as columns of a matrix. And if you do this, the output is going to be a matrix also. So you can have this as a general form of our neural network, and the loss is just computed as the matrix that you obtain at the end, the matrix of the target values, that is also a matrix, all the target values, and this operation here. Why I am showing you this? Because I'm going to simplify this in the next slide, because here is where you can win for GPUs, yes? GPUs for the win here. Why? Because GPUs were made to perform matrix multiplications. And why matrix multiplication is important? Because GPUs, the only thing, not the only thing, but the main thing that the GPU has to do is to have a 3D model and project that 3D model in your screen, which is a 2D screen, two-dimensional screen. So the way in which you project stuff from 3 dimensions to 2 dimensions, for any dimensions to any other dimension, is just by multiplying vectors, positions, by matrices, projection matrices. So the GPUs were created to do matrix multiplications and some other stuff. So if you use GPUs here, you can do, if you're a computer scientist, you know that the matrix multiplication is a very costly operation. It's like cubic in time with respect to the dimension of the matrix. But this is in a computational model in which you have a single processor. But if you have a lot of processor, in particular a processor for each one of the position of the matrix, then you can do this like in constant time. So if you use GPUs to compute all this, the complexity of computing all this equation is just proportional to the depth of the network, to the number of layers. So that is a change in the way we see this stuff. But for now, and for simplicity, we will suppose that we have just one vector. Yeah? But in your mind, you can always think that we have as input and as output, not just one vector, but all the vectors. In the extreme case, all our data we will pass through the network. So far, so good. Also, given that we have only one example, the loss is going to be just the error between y and the target. So we were doing all of this, to just check or just try to understand how we compute the derivative of the loss with respect to one of the parameters. And the parameters that is far from the loss is the parameters in this matrix here. So we want to know how to compute this derivative. So for this is going to be useful to have a computational graph. What is a computational graph? It's just a transformation from this representation. Look at this representation. This is also an animation, yes, to this representation, yes. So you went from this to that representation. Well, what is the difference between the two representations? It's just we are putting a node. This is not a neural network. Okay, this is a neural network, but not a network in the sense that we have perceptrons for nodes. Here we have nodes for variables. Yes. Here we have like weight matrices, functions, and intermediate values. In the computational graph, we have nodes for intermediate variables that are like accumulating operations from the previous nodes. So for example, this U1 here is a node to represent the multiplication of this weight matrix with the input X. And this node H1 here is just the application of F1 over U1. So this is that is why it's called the computational graph. So you have this part here, all this part here is representing these equations. So we have just an intermediate variable here. This part here is represented these equations, and then the loss is represented as the final operation, as the error function between y and t, which is the target. Yes? So still we have the problem. How do we compute the derivative of the lost with respect to the values here? And the computational graph is going to be very useful for that. So that is what we want to compute. And if you concentrate now, you will know how backpropagation works, and then you will be good for the rest of the KHIPU. So we want to compute this, the derivative of the loss with respect to W1. For now, just imagine that W1 is not a matrix, but a scalar value, just a parameter. That is what we want to compute. And if we look at this computational graph, and we interpret this as a function, we know that U1 somehow accumulates the importance of these two variables with respect to the loss. What I'm meaning here is that you can think that the loss depends on U1 and not on W1. The loss just depends on U1, and U1 depends on W1, which is kind of a composition of function. And if you want to compute the derivative of a function that is a composition of two functions, you can use the chain rule of derivatives, la regla de la cadena. So in order to compute the derivative here, you can first compute the derivative of the loss with respect to this node, and then you compute the derivative of this node with respect to this other. And this operation is very simple, so hopefully you will be able to compute this derivative easily. But now you have the other problem, how to compute this derivative. So the interesting part is that we break the problem of computing the derivative of L with respect to W1 into two problems, two derivatives. So we have the problem now. How do we compute the derivative of L with respect to U1? And if you're a computer science student, you say, okay, this is kind of a recursive procedure, yes? So you can do the same now. You can say this is equal to the derivative of L with respect to H1, and then multiply this with the derivative of H1 with respect to U1. This is just chain rule of derivatives, like second year engineering degree. If you don't know derivatives, you can like learn chain rule. It's very, very simple. It's just this, nothing more. And we have the same problem here. We have to compute the derivative of L with respect to H1, and then we can break this into derivatives, and so on and so forth, the same, until we reach the last step, yes? We have the derivative. We want to compute the derivative of L with respect to Un, and then we can break it into the derivative of L with respect to Y, multiply it by the derivative of Y with respect to Un. And finally, we reach a derivative that we can actually compute. This is something that we can compute. So just as a very simple example, toy example, if the error is just this function here, is t minus y squared, then if you want to compute that derivative, it's just the derivative as you know it. Yes, it's nothing strange here. And you can compute that derivative, this function. You can take the value of y, the value of t, evaluate this function here with an actual number, and then put that number here. And if you put that number here, you only have to compute this derivative. Yes? And as another example, if g here, you have to compute the derivative of g. If g is the logarithm function, for example, then the derivative is just 1 over un. You can put the value of un there, evaluate this expression, and then you have the derivative of LUN. And then you can repeat this until you reach the first one. So you have here, recursively put all the numbers here. You put the number of the derivative, like the straight derivative between U1 and W1, and then you have the derivative of dl with respect to W1. This is what is called the backward pass of the network. So the forward pass is when you put the numbers and you obtain the output. The backward pass is when you compute the derivative of the weights in the other direction. So we only have the derivative with respect to W1, but what if we want to compute the derivative with respect to W2? And this is where the magic happens, yes? So this can be break into the derivative of L with respect to U2 times the derivative of U2 with respect to W2. Then we need only that derivative because we already compute this. In the previous iteration, we already compute this, so we have that. And the same with Wn, yes? We have this, we only need that derivative. We already have this one, and we compute that. So in a single backward pass, so just going backward in the network, we can compute in a single pass all the gradients, all the derivatives with respect to all the weights. Why we are able to do this? Because the derivative of W1 with respect, the derivative of W1 from L and the derivative of W2 from L, they share a path from L. This is kind of shared path. And when you have these problems that can be decomposed into shared problems, you use this notion that is dynamic programming. What we are doing here is dynamic programming. We are using values that we already compute to compute new values in the derivatives that we need to compute. Yes. 5 minutes. Wow. So given that we have 5 minutes, there is a lot of details here because we are computing derivatives with respect to matrices. We are not computing derivatives with respect to values. So there is a lot of stuff here. What is this multiplication? This is not a multiplication. It's kind of a tensor contraction and stuff. And you can see all the details in my course, which I have less here, and a lot of more of functions and equations. And I will leave you this playlist here. So in general, we will have more complex computational graphs. And if you see at the graph before, every one of the nodes has just one arrow out. But in general, you can have many arrows. So the computational graphs can look like this. And in this case, we just use the generalized way of using the chain rule. So if you want to compute the derivative of L with respect to U, and U affects L via V1 to Vk, then you just have to sum all the derivatives. So in this way, we can efficiently compute all the derivatives in a single pass, no matter how the graph looks like, as long as it contains no cycles. So backpropagation works for any computational graph as long as the graph contains no cycle. So as a summary of this part, backpropagation is just aggressive use of the chain rule plus dynamic programming for efficiency. So these are the two topics. So you have to know what the chain rule is, and you have to know what the dynamic programming is. These are two very, very important tools in deep learning. Putting it all together, we have a single forward pass to compute the loss. We have a single backward pass to compute all the gradients. We perform one step of gradient descent, and we repeat this. So this is the main building block for training neural networks in details. Not really, really difficult, yes? And it's the same loop that, for example, OpenAI used to train ChatGPT with some other whistles. So just some details, because I have 3 minutes. We only use G as a general term, but G is usually the softmax function when you want to compute the output. And the softmax function is just a way to take a vector and convert this vector into probabilities, like numbers that sum to 1 and all of them are positive. And in a way that the probability of the maximum number in the vector get closer to 1. And you have the formula here. And the error function is usually the cross-entropy function. Yeah, actually, it's always the cross-entropy function. The difference is that the cross-entropy function take different forms depending on the function that you are using. And the cross-entropy function is just a standard way to measure the difference between probabilities. And luckily, in our case, the function is really, really simple, which is just minus the logarithm of the y vector, the output vector, value in the correct label, the label we were expecting. So it's very easy to take derivatives of all of this because the functions are very simple. Just two more notions. We usually use batch training. What is the meaning of batch training? Is that to compute the loss, we want to take the average of errors of all the training data, but it's too inefficient to use all the data in every forward or backward pass. Because most probably now you're using tons and tons of data and you cannot fit that data in your GPU or TPU or whatever. So you use batch training, which is which makes the gradient descent to be more stochastic, to have more like noise. So in each pass, in each iteration, we sample a batch, we sample some number of training examples, we estimate the loss. We don't compute the loss, we estimate the loss and the gradient with that batch, and we repeat this. Let me just go to regularization just a little bit, because regularization, if you took a machine learning course, you will be thinking of what about overfitting and that stuff, yes? Right now, we have a very simple way of trying to minimize overfitting, not minimize, but get rid of it, trying to get rid of it. And this is a very simple and clever idea, is that when we are training, we can make the life of the network difficult by just turning off some neurons. So during training, we just not use this network to train, but we use this network to train. We just turn off some of the neurons. And with some other examples, some other batch of examples, we turn off some other neurons, perceptrons. So we repeat this, turning off random neurons in each training step, random neurons. So in that way, the training is difficult for the network, but when we're using the network, we turn on all the perceptrons, so it's more easy to make a prediction. To sum it up, that's what we covered today. There are several other details that you have to cover. You will have a lot of lectures with some other details, but I wanted to give you a huge overview, very basic, shallow overview of what it is. Just to give you, to motivate you about KHIPU and KHIPU impact, in 2019, it was the first KHIPU. We were able, in the Universidad de Chile, where we were working, to give, gracias a KHIPU, given KHIPU, we were able to train the first Spanish BERT model, which is kind of the first large language model in Spanish. It was a thing at that time because almost all the big networks were either in English or Chinese. At that time, there were not a huge network in Spanish. And we did it with a gift that Jeff Dean gave to the people that attended KHIPU that year. KHIPU 2019 was just 1 week after GPT-2, which is like a earthquake in research, yes? But anyway, it was interesting to do that. And even today, this model is being used by, for example, here is a person in the INE, the Institute of Statistics, National Institute of Statistics in Chile. They cannot just put their data in Amazon Web Services. They have to run the data in their machines, and they are using Beto in that way. Why I'm telling you this is that during this week, a lot of things may happen, maybe not like TPU credits, but maybe some, I don't know, usage of Gemini, and you can start a startup with this usage that they are going to give you, or you are going to make some important connection with some other student and with some researcher. So take advantage of KHIPU. It's going to be an amazing event. So thank you very much. We also have a coffee break, and we'll be on a coffee break, and we'll be. If someone wants to ask in Spanish, I can understand Spanish. And barely speak Spanish, Chilean Spanish. Good. You?
Thank you, Jorge. Okay, but there is no coffee break now. No. But almost. So we have the spotlight talks that are 15-minute talks, and we have 2 of them, and then we have coffee break. So, I would like to introduce Rodrigo Diaz from Argentina. Rodrigo holds a PhD in physics, me too, from the University of Buenos Aires, and currently serves as a staff research at CONICET and professor at the Universidad Nacional de San Martín, where he spearheaded the development and now directs the University Innovative Data Science Program launched in 2022. Let's welcome Rodrigo.
Thank you very much. What a disappointment. I thought it would be coffee break. So thank you for the invitation to be here. I'm very honored to be able to give this talk. Let's see if this works. No? Yes. 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 Oh, exoplanets. No. Wait. Oh gosh. Excuse me. Let's do these as well. Yeah, good. All right, so I was saying thank you to the organizers for the opportunity to be here to give this talk about spotlight research in Argentina. I'm a researcher at UNSAM, where I do astrophysics, and I've also started very recently a position at IDBA, the Institute of Technology in Buenos Aires, as head of department of the Digital Systems and Data Department. So I was asked to give an overview of the research we are doing in our institutions. So my plan is to spotlight some of the projects at UNSAM, and then very quickly at the end show something of some of the research people are doing at IDBA. I have to apologize beforehand. This will be very sketchy for some of the projects, but because there are many of them, but do feel free to come and talk to me, vengan a hablarme, and maybe I can tell you more about it or get you in touch with the people who are really doing the work. So let's start with UNSAM. UNSAM, there's many things I could say about this beautiful university in the metropolitan area of Buenos Aires, but I will go straight to the data. This is a university which is founded in 1992, so it's relatively young. It has around 25 active students, and it has strong research profile, especially in the biosciences, where one of the recent highlights is the production of a vaccine for COVID, fully done, completely done, entirely done at UNSAM in Argentina, actually. Thank you. So let me start with some highlights and spotlights about AI for medical research. So the first is by in the Centro Universitario de Imágenes Médicas. This is work led by Martín Belsunce. You have the web page there. You can go and see. And what they're doing is working on segmentation using convolutional neural networks, basically to detect the different muscles in the spine and being able to compute the mass. Do I have a pointer? No. I don't have a pointer here, no? Okay, that's okay. So basically to try to detect and measure the fat infiltration of these muscles. They have done some very interesting work and even taken this to the next level and doing some translational work with doctors and using this on actual patients. Next is in work by Diego Mateos and Santiago Blas, who are over there somewhere. And I will not tell you much because I don't understand the work very well. And also because there's a poster 340 that you can see on Wednesday. So Santiago is here, and this is work done in collaboration with the University of Litoral. Thank you. Gracias. Perfecto. Buenísimo. It's a trick. Yeah, it's not strong enough. Okay. So next, let me move to another lab at UNSAM. This is the Physiology of Action Lab, and this is led by Valeria de la Maggiore and also Agustín Solano, a postdoc there. You can see the website also for more details. Basically, they are doing sleep studies. They want to understand how, if it's possible to detect in real time when a person is falling asleep. And this has a lot of applications, basically to help drivers, truck drivers, and bus drivers. And for this, they have all these time series. Basically, the basic approach is that an expert would look at hundreds of pages of this time series and label each stage as one of the different stages of sleep. Here, down here, you don't see the pointer, no? I don't see the pointer, so I guess you don't see the pointer either. And now they're exploring different AI and machine learning methods to do this automatically. And what they are very excited about is this rocket model for time series studies. There are many other things at UNSAM that I would like to tell you about, but I don't have the time. There's actually a full center for AI in different areas, so it's an interdisciplinary center. And we are doing research work, but also applications, producing tools and services for different government parts, and also private companies. And also we have a very strong training program for companies. So come to talk to me if you want to know more about this. There's really a lot going on at UNSAM. But I'd like to, of course, concentrate on what I do, which is exoplanets. Jorge said that people would get weird looks when they were saying that they were doing AI during the winter. Imagine when you say you're trying to find life somewhere else in the universe, so you also get weird looks. But of course, I'm not doing this alone. This is my small group of very talented young people. As you can see, there are people from different disciplines. We have computer scientists, physicists, astronomers, and we are doing research in this interface between data science and astrophysics. So I will highlight a few of these results and research, and then go to the last part of the talk. So this is something that it's work by Juan Serrano Bell, a PhD student of mine. He's trying to improve on the instrumental performance of our instruments. They are not perfect. They have these systematic effects, and so we are modeling this with machine learning models. And there's a poster that you will see today, if I manage to get it printed by noon, in poster 124, and I will be there to present it. But of course, it's not only the instruments that do not work correctly. It's very hard to find exoplanets, also because we have this thing going on. How's that for an animation? That's the sun. That's an actual video, actually, of the sun. And you can see there's many other things going on in a system. It's not just a planet going around the star. The star itself has a lot of activity. And so we have to dig in the noise produced by the star in order to find the signals produced by the exoplanets. So this is one of the most challenging aspects of exoplanet research these days, and we are trying to bring machine learning into this. We're not the only ones, of course. And this is work we've done with Agustin Nieto, another PhD student, very, very close to graduating, where we have created a very simple, as you can see, if you understand this notation, this is a very simple CNN in which we input the data from our observations, and we try to distinguish whether there's a planet in that data set or not in the presence of this stellar activity noise that I've just shown you. What we have shown is that this approach is superior to the traditional method, which I will not describe here, but it's based on frequentist p-value statistics, which is the light blue line. And you can see that the CNN outperforms this method, especially for low amplitude signals, which are the more difficult to find, and also the more interesting ones, because these are related to smaller, less massive planets, so more like our planet. So this is very exciting, and something that we really like about this result is that we can see that the recall, meaning the the amount or the fraction of planets that are recovered by the traditional method is almost constant. You can see this on the left side of the screen, while for the network we see a decrease there when the signals have periods of around 30, 40, or 50 days, which is related to the activity of the star. These periods are the typical periods, the typical frequencies where the signal, where the noise appears. Meaning that the network somehow learned how to be more careful in that period region, which of course brings a better precision with it, right? So this is very similar to what we actually do when we observe the data and we see there are signals at those periods. Then as humans, we tend to be more careful if the signals are around those periods. So we can see now that the CNN is doing something similar. So let me show you another aspect of the work we're doing in the team. So this is work by Leila Asplanato, another PhD student in the team. She's working on different aspects of societal problems, and this is related to inequality in the secondary level students in the district of San Martin, where the UNSAM is located. And this is work. This is really interdisciplinary work doing with educators, Eduardo Langer and Silvia Greenberg, also from UNSAM. And we're working on a data set of 98 secondary schools in the district. These are all the secondary schools in the districts. And we are doing some very simple clustering techniques to get insights from this data. And it is very interesting that we found that there are two types of schools. After the great divide of the public and private administration, which is the very first, very clear divide in this data set, we find that there are two types of schools, and this is what we wrote. One of the clusters seem to have a more inclusive response, allowing and encouraging students to remain in school even in the face of failure, while the other cluster of schools seem to be more have a more expulsive behavior. And we see this in the publicly administrated schools as in the private ones. So this is a different type of thing that we found. And this is very rich for our colleagues, which from this they can go and see which schools are in each cluster and understand this and compare this with more qualitative resources. Finally, I have just a few minutes left, so I would not like to leave without telling you a bit about ITBA. ITBA is an older university. It's a private university in Buenos Aires. It's very prestigious in many areas of engineering. It has this project-oriented education, so students do things from very early on, and they have a very early connection with industry. It's undergoing a very strong change and trying to perform more science and more academic work. So there's also many interesting teams working here. I will only highlight work done in the Neurotronics lab led by Rodrigo Ramele. Also, you have the website there. He's working on brain-computer interfaces. Actually, they have started a startup very recently because they found that they could stimulate just by introducing some type of very low noise during sleep. They could stimulate one type of brain waves, which is good for health, and it's supposed to help you release many of the toxins you accumulate during the day. So it's a very encouraging and promising approach. They also have sleep research at ITBA and a lot of robotics. They have developed many types of robots for elderly care or for rehabilitation, pacemakers, and so on and so forth. There's also work done in people doing control, on research on control and autonomous vehicles, and much more. So as I'm out of time, I'll just leave my final slide. Please get in touch and come see me during coffee or send me a line. Thank you very much.
Thank you, Rodrigo. Now is the turn of Andrea Lara from Guatemala. Please. Andrea is the director of the first biomedical engineering academic program and research laboratory Biomed Lab in Guatemala and director of the Biomedical Engineering Institute at Universidad Galileo. She holds a PhD in biomedical engineering from Graz University in Austria. Thank you.
Hi, I'm just going to set this really quick. Okay, so there it is. So, good morning, everybody. My name is Andrea Lara, and it is my pleasure to be here and present some of the AI landscape that we have in Guatemala and also some of the work that we are doing. So, as it was mentioned, so I come from Guatemala and exactly from, from Guatemala City, and I work at Universidad Galileo, where I'm the head of the first biomedical engineering research lab. So to give you an overview of how is the landscape of AI in Guatemala, I put it like in three main blocks, talking about education, industry, and research, which is what I'm gonna focus later. So if we talk about education, most of the programs are mostly related on AI applied to different business, applied to data science, and mostly on its applications to marketing. And this is also reflected in the industry, where here I refer to the companies that already exist where they are working with AI. So here, for example, we talk about marketing, business intelligence, and how AI can be applied, well, to the industry. And finally, research, which is what is interesting here. And here we have like three main blocks, which is agriculture, because our industry is mainly based on the agriculture. Then we have education and healthcare, which is most of the research is based on the necessities that we have as a country. And finally, the cement industry, because it's kind of big. But in general, I'm going to talk about these three main areas. And I'm going to start with agriculture. And I have a pointer over here. Okay, here it is. So here on the top, I have some facts. So in Guatemala, the biggest agricultural industry is basically sugarcane, coffee, and bananas. And here, most of the research is based on how we can solve some problems related to computer vision problems. So for example, we want to visualize and analyze how the plants are growing, or if they have some kind of disease, or any other thing that can affect the growth of these plants. And then there are other problems where we want to, for example, optimize the use of some specific, for example, fertilizers or pesticides use. And this is a project that one of my colleagues is working. It's in agriculture, and here what we have is a plantation of sugarcane. So it's here, so you can see it's kind of big. And what they want to do is that they want to optimize the use of fertilizers in this plantation. So they want to use it only where they can see the sugarcane, and they don't want to use it on other plants. So for example, wheat that looks over here, that I don't know if you can tell, but it looks kind of different. But there is also other plants that are over there that look like the sugarcane, like this one. So the question is how we can characterize these specific plants so we don't use the fertilizer there and we only use it on the areas of interest. So this is one example and can be applied to other areas like bananas or coffee. Then we have education, and here most of the research is how can we use AI to provide tools that can really solve the problems that we have as a country. And again, here on the top, I have some information. So these are statistics from the educational ministry, where it says that in the national system, we have around 26,000 teachers for a total of 3 million students. So that means that on average, we have like one teacher for 114 students. And of course, as we can imagine, this can affect the quality of the teaching and also the experience for the students. So the question is, how can we use tools like AI to improve this situation? How can we give them some tools so they can learn in a better way? So for example, there is a lot of research on how we can use virtual tutors or assistants to help them on this teaching experience. But also, as we are a country with different languages, most of the content that we get in schools is in Spanish. And the question is like, can we improve the experience by maybe translating most of this content into the Mayan languages? Just in Guatemala, we have 22 Mayan languages. So the question is, how can we improve this experience by translating this information? And then we have healthcare. And here again is some statistics. These are the latest that I could find. So in general, in Guatemala, most of the population, it's located or in the city or in the rural areas. However, if we talk about the healthcare professionals, it's not the same. So for example, here it says like 26% of the healthcare professionals live in the rural areas. That means that the rest is in Guatemala City. And Guatemala City is not that big, but the country is bigger. So it's like, how can we get to these professionals? And it's something that we really need to address. So again, the question is, how can we use AI? And for example, there are some research on, for example, using AI chatbots just to solve some of the basic questions on medical questions, or for example, on mental health. But then there's other applications, which I'm gonna show, that are most related on how we can improve that access using AI. And this is where my lab comes. As I said, this is the lab that we have at Universidad Galileo, which is called Biomed Lab. And here what we are doing is that we are mostly focusing on developing tools that address the needs of our healthcare systems. So the idea is that we want to collaborate with local hospitals, however, most of them are in the city. So we also want to work with local providers. So it's like, how can we give them tools, for example, to the midwives, other nurses, which are the providers of these healthcare services in the rural areas. And if we talk in the technical side, we are focusing on medical image analysis and assistive robotics. And here is an example of one of the projects that we are working where we're using AI. And the name of the project is Natalia, so Natalia. And the project aims to improve the access to prenatal care in rural areas of Guatemala. And again, the idea is, how can we close that existing gap that already exists between the pregnant women that are in the rural areas and the experts, which are the obstetricians, that are in the city? So how can we close that gap? And it's not only in terms of because they don't have the means to go to the city, but there are also other barriers, for example, cultural barriers, language barriers. So how can we really get them the services that they need, for example, prenatal control studies that are required during the whole period? And that's why we are working in close collaboration with the midwives of the rural areas of Guatemala. And what we're doing on a first stage was to test this tool that uses AI. And basically what it does is that simplifies the acquisition of ultrasound studies for them later to be assessed by a professional, in this case the obstetrician, and allows them to get feedback from them without traveling to the city or without going to this hospital where they don't want to go. And here I have a video to show that. So for you to get an idea, so this is like how it looks, most of the rural areas of Guatemala, and unfortunately, as I said, most of the access to this special services care is difficult. So that's why we're working in collaboration with the rural midwives, where what we're doing is that we are giving them an ultrasound and show them to do blind sweeps, where basically they use the ultrasound over the belly of the pregnant woman, so they don't have to get a specific training, and then they capture all these videos. And the idea is that these videos later can be uploaded to our tool, which is Natalia. And here, what it does now in the first stage is just to analyze these videos and acquire the relevant fetal planes that are required for prenatal control. So what it's doing is that it's identifying, for example, the head, the heart, and other areas of the baby that are important for this control. And yes, these planes are well analyzed by the obstetricians, for example, and then they can give a report and give it back to the midwives. And so this is one example of the project that we're doing. We're doing more like in that line, but just to get you an idea. And just to close, I would like to mention that, of course, as in many other countries, we have challenges that we really want to address, and that, So, for example, funding, this is one of the challenges that we still have as a country. I'm not just talking about my lab, but I'm talking as Guatemala, because I was giving you an overview. So one of the challenges is funding. Then another big challenge that we're facing is how can we retain talent? Because most of the talent doesn't stay in the country. So even that we are like helping them to develop tools and to get all the necessary skills, the problem is that as a country, we do not really have these opportunities where they can do research. So that's why events like this are important, because then we can see like if we can start collaboration with other countries, with more Latin Americans, in some way we can grow the opportunities they can get. And well, not everything is bad. So there are also, what can we do about it? So, and this is from our side, from Galileo, but for example, from my lab, we're really working on how can we create and promote the research community. As I said, it's still a problem, but the idea is like, okay, we need to do something. And one example of that is that, for example, last year we had for the first time in Guatemala, medical image analysis conference, which was never held in our country. So that was a big step, and especially for the students, because they get to see that there is a community and the project and the work that they're doing is having an impact. So that was really nice. And then we're also fostering collaboration between industry and academia, because as in many other countries, this is really well established, but in our country, no. So this is something that we are really working on. And of course, as we are a university, we're training the professionals with the required skills, so when they go outside, they can really perform on those works where, well, they need those skills. And with this, I finish. So thank you very much. And here, if you want to do some collaboration, here's my contact, and also from my lab. So thank you very much.
And now is the coffee break, okay? So, it's one floor up, which in Chile means primer piso. But for some of you, it's ground floor, yeah? So one floor up, there is the booth with the sponsors, then there is the coffee break. And we see each other at 11 here. Thank you.
acá está el USB-C. Ah, mira, hay uno, pero... Pero ahí. Porque hoy no hubo en la primera, no sé por eso. Do you want this, Alfredo, as well?
Sí. Sí. Pero oye, ¿cómo se...? ¿Espera?
¿Lo quería apagar?
Sí. Ahora está apagado.
Hello, hello. Welcome back to the session. It's my pleasure to introduce Alfredo Canziani from New York University in the United States. He's a musician, math lover, cook, and dancer who's currently working as an assistant teaching professor of computer science at Courant Institute of Mathematical Sciences under the supervision of Professors Kun-Yun Cho and Jan LeCun. We've heard those names before. So please welcome Alfredo.
Thank you. Buenos días. Vamos a hablar en inglés, creo. Morning, and what do we teach? What do we talk about today? So I just landed, so I just figured out what you've been taught in 3 minutes before the class. So let's start with a recap of the things you saw before, maybe 5-10 minutes, and then we move forward towards more advanced topics. Let me know if you think it's too slow, too fast. You should try to interact with me. Moreover, one thing that was missing, I'm also a YouTuber. All my videos with Jan are available for free on YouTube, where basically our deep learning course is available for whoever wants to watch it. Moreover, I'm writing a book, which is coming up, I don't know, soon, hopefully, maybe. It depends. If I'm teaching new courses every semester, it's going to be a bit hard. Anyway, so we're going to be talking about classification. Why classification is so important? Because basically these days, many of the applications can be seen as a classification task. For example, next word prediction. It's too noisy. What happened? Okay. When we do next word prediction for a large language model, we are just doing a classification, what is going to be the next word in a sequence. But let's start with the basics again, very quickly, going through. So what are we trying to do here? We're going to start with, for example, 2D points that are represented in this chart, and then the color might represent the class. So we have 3 classes here. To make things a little bit more spicy, let's actually add some noise such that you can actually see the distinct points. And so the idea of classification would be to find some decision boundaries that are splitting those points in specific partitions. So let's use a Perceptron 1957. And you're going to get these amazing decision boundaries, which are, unfortunately, crossing our data points in different points. And so how can we fix that? Well, to me, there are 2 options here. One option is the one of undoing the warping of the data, which is actually what I'm going to be showing you in a second. That was just a backward animation of the spiral. Or the other way, usually you see this approach here. You can see how the model warps the linear decision boundaries such that those decision boundaries are going to be following the data. But you can either linearize the data or you can unlinearize the decision boundary. Let me show you an actual video where I do this for a neural net. With a neural net. So in this case, we're going to be starting with 5 different spirals with 5 different colors. I send them through a neural network that has 2 input units because the points live on a 2-dimensional space. They go into a 100 hidden layer, like a hidden layer of 100 units. I have a positive part, like a ReLU. Then I go up to 5 different classes. Before going to 5 classes, I'm going to be going to 2 classes and then to 5 such that I can show you things on the screen. What you can see basically here is going to be a linear interpolation between the input layer, the 2-dimensional space, and the 2-dimensional embedding layer. And then what the network does in this single, very fat, large hidden layer is going to be unwarping the spiralized data such that it becomes linearly separable, and therefore the last final classifier is able to chop those 5 different regions with basically lines. So now we are basically at the other end of the network. And here you can see basically how the model splits the data points with just linear decision boundaries because that's what we have at the last layer. And so this is the view of the data that you feed to the model. So if you look at the neural network, the head of the neural network is going to be on the bottom because you have low-level features. You provide your data that is basically warped. As you go through the model unwarps the such that at the higher level representation, everything is actually spread around and very nicely linearly separable. How did we do that? Well, we just trained it with a softmax and whatever. So again, you covered this before, but I just wanted to show this picture. Basically, the network is learning how to manipulate data such that it's going to be performing our task with ease, which is, in this case, classification, which means figuring out what is the color of the specific initial points. Okay? No magic, right, so far. Now maybe a little bit of magic. So just going very quickly through how this fully connected layer is built. This is not called MLP or multi-layer perceptron because a perceptron has a binary activation function. So there are no such things as MLP, multi-layer perceptron. We just call them fully connected. Anyway, I'm pedantic, I know. We have an X. Yeah, you're going to figure out I have many of those such things. But we have at the beginning and the pink bold X at the bottom, which is going to be sent inside something I call a predictor. The predictor gives me the hidden representation of my target. So the hidden representation goes inside a decoder, which gives me something that is like almost a Y. That's why there is a tilde on top of the Y. So I have a Y, which is an approximation for my true Y. So what is my true Y? Is going to be, oh, well, it's not in this slide. Next slide. So how do I compute this hidden representation? It's going to be just an affine transformation of the input. And then I might have multiple hidden representations. The F and G are simply some nonlinear function. For example, the positive part, or also known as ReLU, or some hyperbolic tangent. So I have my first layer, first, hidden, second, whatever. You have a very deep network here. Anyway, how to compute the first unit? We're going to be multiplying all the input units, which are in this case 5. So I have a vector of 5 units. I multiply each single value by a specific weight. I sum them up. I add the bias. I apply the nonlinear function. That's going to be my first hidden unit value. How to compute the second hidden unit? I do the same. I take all my 5 different inputs. I multiply them by some 5 scalars. I multiply all of these. I'm just doing inner products or scalar product. What happened now is very bright. Thank you. Now I sum up all those things together. I add the bias. I apply the nonlinear function. I have my second unit. I do this forever, everything, and you can see how I can draw things with PowerPoint. Anyway, I can collect all those arrows in my first W1 matrix. Then I can do exactly the same for the second layer, where I try to copy and paste. Doesn't work because it's going to be 10 to 10 before it was 5 to 10. Anyway, I spent quite a bit of time making all those arrows, but they are just my W2 matrix. And so you have basically a bunch of linear operations that are basically rotating your input. The 5-dimensional input gets rotated and projected into a whatever 10-dimensional input space, and then it's going to be sent through a nonlinearity. Why do we have nonlinearities? Because if you have linear affine transformation, affine transformation, affine transformation, affine transformation, affine transformation, you eventually have just a single big affine transformation, which are not very useful. Instead, if you add these nonlinearities, then the magic comes into play, and then very interesting function can be derived. Anyway, more arrows, more matrices, and the pointer doesn't, okay, it works, and therefore we have the end here. All right, so how do we actually, so let's go into a little bit of details. These are my notations, so you're gonna get used to a little bit. X goes inside the predictor predicts the hidden representation of my target. It goes inside a decoder, which predicts this approximation of Y, my Y tilde. So how do I know where to put this Y tilde? Well, I can compare it with my blue ball Y. My blue ball Y is going to be my target, the thing I want to learn. And I want to map that having X going through the model, and then I force my Y tilde to be close to my Y through that box, which is going to be like a spring that is trying to get my Y tilde close to my Y. These are some equations. We don't care. These are something. The soft argmax is actually the true function, the true name of the softmax function. And then we want to actually think about the fact that, yes, the Y tilde is going to be this function of the input X, but what you really want to think is that the Y tilde, our output of the model, is going to be some projection down from a large dimensional space D. So we go from n 2-dimensional points to my 5 points, 5 classes, but in the middle, we actually expand this into a 100-dimensional space. It's very, very important that we are actually going to intermediate, very large dimensional space because things are very easy to optimize. And that's actually very important since we are using gradient descent to learn these models. All right, so one more slide about the basics, and then we move forward to a more interesting type of architecture. So, okay, energy. What is this energy? So I will just mention this fact that we like, me and Jan, to have this additional type of interpretation of these models. In this case, the energy is going to be that dash box that englobes everything besides the inputs. In our case, the inputs are X and Y. Both are provided to the machine for the machine to learn things. And so my energy, F, represents the level of incompatibility between my inputs, X and Y. And it's, in this case, is simply equal to my single red box inside. And so this is exactly the distance or the divergence between Y and Y tilde. So my level of incompatibility of my inputs is a scalar value, and which is going to be represented here as the distance of my prediction to my target. Okay? So once I train my model, we expect to have a very small distance between my prediction and the target. Therefore, if I train my model and I test a pair that comes from the training set, the energy of the training pair should be a low energy. Instead, if I switch, let's say, the target, and I have a X with a wrong Y, the energy should be high, because the prediction for the wrong target would give me a large distance here. And therefore, the energy will tell me, oh, this is an incompatible pair. Maybe it was mislabeled, maybe something else. Or you can also use this energy to change the input such that it's going to be more compatible with this. So we can use gradient descent in the energy to change some of the variables. This is pretty interesting, I think. Again, this is kind of advanced, tangential, so let's move forward. Last slide here, we have this final definition of the soft argmax. If you want to know why it's called soft argmax, I have slides on that. Check on YouTube. I'm very vocal about this. Anyway, the soft argmax is a relaxation of the argmax function, which is the one hot. You can think about a one hot vector representing the index of the maximum value is like a probability distribution, which is 100% on the maximum value and then 0 otherwise. Softmax instead is not one hot. It's going to be something more relaxed where you actually distribute this probability around. Yes, people call it, they forget the arg, but anyway, I don't care. My loss, the curly L, is going to be the average per sample loss. It's going to be telling me how bad my weights are for my old data set. And it's going to be, again, the average of this per sample loss, which is going to be how bad my weight is for my specific sample X and Y. In this case, we can choose to have the loss equal the energy, so nothing new in this slide. And this is a choice. That symbol with the arrow is some decision I make. We can choose many different losses to do classification. This is one choice. And then finally, we had that the F, the energy, was equal the only box inside the big box. So far, F just equals C. And then we have here some specific choice for the cost as well. So we have two choices. This is my first choice, the fact of using the loss equal the energy. And the second choice is to choose the distance, the metric. I'd like to use the divergence between the Y and the Y tilde. In this specific case, I use the the cross entropy or the negative log probability. How does that work? You plug inside the correct prediction, you're going to be getting basically 0. You plug inside the wrong prediction, you get basically things to go explode. How do we train this stuff? We're going to be finding the gradient of this loss with respect to the weights, and then we're going to be just going downhill such that we can figure out how to find a minimum. Okay? You already see this before, so I'm going to be just very nicely going forward. One thing, how do we learn? So that's, we learn through gradient descent. Gradient descent is what changes my weights following the gradients. How do we compute the gradients? We use something called chain rule in mathematics, or in deep learning we call backpropagation, same as chain rule. Okay? Gradient descent allows me to change things. Backpropagation allows me to compute gradients. So this was like a recap of what you have seen in the previous lesson. Moving forward, we would like to figure out how to possibly handle vectors of different sizes. In this case, no, in this other case. Yeah, in this case, we saw that we were mapping a specific length input vector of size 5 into some other 10, 10, and something else. How about if I have a variable input length? How do we handle that? So, for example, X could be a sequence of words, the words I'm telling right now. And so if I have different sentences, if I make different sentences, sentences might have variable length. So how can we handle variable length network? We have to actually use something that is called weight sharing. We have to use the same weights throughout our sequence because it's likely that the statistics of our sequence is going to be some sort of stationary, so we're going to be observing the same statistics throughout the entire sequence. And so we have to start using, we can use different type of models. One model is the one that Jan devised in 1999, which is called convolutional neural networks. It's been used for mostly images. It can be used also for sequences. It can be used on any type of grid structure, 1D grid, 2D grid, 3D grid, and so on. I won't be talking about this today. I will be talking instead of another type of system. This system here is if you're a physicist, you would call it a non-dynamic, so static system. You have the output depends only on the current input. Instead, if you have a dynamic system, you have a system that has a memory inside. It has an internal state. So let's have a look very, very quickly to a possible neural network with internal state, and then we're going to be actually moving away from that to the actual final architecture that is most of your interest, perhaps, that is the attention-based transformer network, okay? Tell me if you want me to change the topics, because I'm just improvising this lesson, so I can completely change it based on your feedback. But if you're quiet, then I don't know what you want me to do. So I just keep with this unless you complain. Okay. Oh, yes, I have other 50 lessons, so in case you want to listen to me more, you can just request I'm available on demand or just play on YouTube, right? I'm here the whole week. I don't mind talking. Recurrent neural networks, what is this stuff? Yes, so people point out that recurrent networks are not used anymore because they've been replaced by other architectures. It's not true. This is a fundamental item. You have to understand to have one more let's say building block, like Lego block in your dictionary. If you know words, you can put together sentences. Even though you won't be using these words very often, but you still need to know the words in order to be able to understand what sentences might mean, okay? So let's figure out these words here. Recurrent neural net, handling sequential data. People also try to use recurrent network for handling images, other things. That's bullshit, don't do that. This is just for sequential data, okay? Then you can do anything you want, but then, you know. All right, so recurrent network diagram, how does it work? We're gonna be starting again with my input X. This input X goes inside as before. Predictor. Predictor, once again, predicts the hidden representation of my target. Why do I call this predictor? So if this is the X space, I can go from the low-level X space to the high-level encoded X space. Then in this other space here, I have my Y space, and then I can encode this one. So if I have a hidden representation here, I can go down to the low level through a decoder. But to come up to generate this hidden representation from the X, I need a predictor that allows me to move from this side to the other. Just terminology, just notation, okay? So we have this predictor that predicts the hidden representation of the target. There I have my hidden representation. And the hidden representation goes inside that weird thing there that is the unit delay. If you have done digital signal processing, I'm just using the Z transform. If you don't know what I'm talking about, it's okay. So this is just unit delay. I put inside H at the index T, and it returns the H at T minus 1. So it has a one memory memorization, one hop. It keeps in mind what happened before. It returns afterwards. Notice we have a discrete clock. It goes at integers, 1, 2, 3, 4. So maybe actually I should have replaced the T with lowercase n. I had my professor from engineering that are complaining about this stuff. I fixed it in the book. All right, so we have also to specify what is the first value of this unit delay. So the first value is going to be this H naught, which is my first hidden representation. We can learn it. We can set it to 0. You can do whatever you want. Otherwise, at the beginning, we connect this down. So I feed to my predictor my initial H and then my X. Otherwise, I'm going to be switching this switch to this connection. And then I'm going to be having delayed outputs. So basically, as you can see, there is a cycle. with a unit delay inside, which is basically allowing our system to have an internal state. So we have a dynamic system. Our output, well, the hidden representation does not only depend on the current input, but also on what happened before. And so in this case, we can build a hidden representation that changes over time, given that I provide one symbol at a time, and therefore we can think about trajectories of hidden representations. Finally, we can decode the H. I'm gonna be getting my Y tilde, and then I have to compare my Y tilde with my blue ball Y, which is my target, the thing that I'd like to learn, and I do that using like a spring, like a distance. Why do I call it spring? Because we like energies. If you have a spring, what is the force of a spring? Have you heard about Hooke's law? Okay, how about what is the work for a spring, or the energy for a spring? Take the integral, right? You're gonna have the square distance. So if you have like a MSC, like a square Euclidean distance, that's the energy of a spring. If you take a gradient of an energy, you're gonna get the force. And so that C basically acts as a spring that is gonna be pulling that Y tilde towards that Y. So we can reason in terms of physical systems. I'm an engineer, so sorry. I go back to real life stuff. Questions, how does this stuff work? I have my initial representation, H naught, the initial state, equal this H0. Can be learned, can be fixed, can be whatever you want. Then I have my update rule, which is going to be the hidden representation, and the index T is going to be the output of the predictor, which is fed with the previous hidden representation in the current X. And then I have finally this decoder fully connected, whatever. Okay, so how does it, okay, big thing. Now I have the big F. Big F was the energy of the system, which is telling me the incompatibility between X and Y. Question, can you guess what is F equal to? It could be like before, right? F equals C, but it's not quite the same as the previous slide because something has changed here that you might not be aware. So let's switch to the next slide, and then we come back once we figure out what happened, okay? So recurrent network, how does it work, right? So we can just have these equations for memory there, and then I put out all my time indexes on the bottom side. And so at the beginning, we have this initial hidden representation that goes inside the predictor together the current X, so previous H and current X. Inside the predictor gives me the current H. Current H goes inside the decoder, generates a Y tilde, which is then compared against the Y through the C spring. Okay, so the Y tilde gets close to Y with the spring. And then I keep going. So I'm gonna have my the current X, which is sent through the predictor together with the previous hidden representation. It gives me the current hidden representation. It goes inside the decoder. It generates a new hidden representation. And then I really had to move here, otherwise this doesn't work. And we have, again, our different target, one more spring, and so on. Okay, so I have one more X. I have the previous hidden representation inside. It goes inside the decoder, yada, yada. You just do a copy and paste. This time actually works. You finished with this current situation. So we have multiple X's happening at different time indexes. We have many Y tildes, our predictions also happening at different time indexes. And then on the other side, we have the final target, which is going to be hinging where we hinge the spring such that the Y tildes are going to get pulled towards those attractors. So again, I use these terms. I hope it's fine. And now, where should I draw the energy? The energy is the big box that has everything inside but the input. So this is my energy. So I will ask the same question I asked before. What is the energy equal to? I have a bunch of those C's. And so my energy is going to be just the sum of all these distances, the sum of all these divergences, or whatever you want to call it, okay? And so if we go back to the previous slide, we're going to be seeing that the final equation was the incompatibility between these two sequences, X and Y, is just the sum of all these costs between the predictions, Y tildes, and the Y throughout all the sequence. And so we have, again, one scalar, which is representing, again, this incompatibility between X and Y. How do we train? We're going to be coming up with a loss, which is a function either of the weight or it's going to be a functional of the energy, such that we can lower the energy of compatible pairs. Okay, so here we have these models that have been used for different possible applications. In this case, we have a single input, and then I have multiple outputs. This could be, for example, image captioning. I send an image to my model, and then I ask to emit discrete tokens, which are going to be representing, for example, words in English. So I have a single X, a single vector, and then it's going to get mapped towards a sequence of words. So I basically add some temporal components, some expansion of this single image. And so I have vectors to sequence. On the other side, I have the opposite. I have a sequence to vector. So we're going to be going from the full sequence, the pink one, towards a single final classification. An example of this could be, for example, sentiment analysis. You're going to be reading a review on Amazon, and you're going to be trying to predict how many stars that review had or something like that. And so you can learn basically the sentiment of that specific review. We have two more of these diagrams. One is going to be this interesting thing here, which we're going to be going to this part actually very soon in more detail, which is going to be a sequence to vector to sequence. So we have a sequence. We compress away the temporal information such that we can now acquire a hidden representation that I like to call a concept vector, which is condense the concept that was expressed perhaps in English. And then the concept vector is going to be sent to a different decoder que va a traducir lo que decía en inglés en español, por ejemplo, ¿no? And so we can have a translation system where you condense English, you have a meaning, y después vas a decompresarlo, a explicar, a escribir lo que quieres en qué idioma quieres, ¿ok? ¿Vale? Bueno, this was the main approach that took away, like it replaced the statistical translation system at Google. And so this was like a really the main way to do translation, like Google Translate was using this stuff. It has some problem. The main problem here is that H bottleneck. We're going to be, again, getting into more about this stuff in a few minutes. Let me show you the last one here. The last one is going to be just directly sequence to sequence. For example, I could have, I'm going to be humming like a tune, and then the other part is going to be writing down the melody for music notation. So instead of just doing transcription of jazz pieces, so if you want to practice, you can just have this system automatically writing all the pitches of the music you're listening. Okay, so back to that the system on the left-hand side. We're going to be going to that part because that's what actually brought us attention these days. And so let's see how that architecture on the left-hand side, which are the limitations, how attention has addressed those limitations, and then how you can just use attention completely, regardless, without having this kind of dependency loop. We have this system, like this feedback loop, that requires a for loop in your model. And then guess what? We are using GPUs that can just parallelize things that don't have for loops. And so that was like a major problem in terms of speed. Okay. And so finally, let's get to the last part. How much time do I have just to know? I can talk forever. I mean, I'm just 20 minutes, amazing. Okay, so we can actually slow maybe a little bit down. Okay, so here we start. All right, so sequence-to-sequence modeling, which is the one that we saw on the bottom left-hand side. And we're going to be trying to use attention to perform something that is called context-based summarization. So we're going to be generating a context based on what we actually we care. So we're going to be generating this concept vector iteratively for every output. Let's see what's going on. So sequence-to-sequence model. This was used a lot in machine translations. And so we're going to be using this as an example. And machine translation maps a source sentence to a target sentence. For example, the source sentence that I indicate with S, going from 1 to capital M, is going to be the sentence, the front door is red in English. And then I'm going to be having, for example, a target sentence. This is my first target sentence, which is going to be going from 1 to N1. It starts with beginning of sentence. Then I have la puerta de entrada es roja, and then end of sentence. So these are the discrete tokens I have to produce, discrete symbols I have to produce. Each of these are simply the output of a classification problem. So you have a dictionary of 10,000 words in Spanish, and then every single time you just do a classification and figure out what is the most likely word that should be appearing there. That's why we started with classification today. Another optional target would be 前面是红色的. Do we have Chinese-speaking people here? No. Usually my classes in NYU is like 70%. Okay, but all right. So I was going to show off my Chinese. Okay, but never mind. I show off my Spanish today. Okay, so how does it work? So we're going to be starting with my source sentence. Again, this, the front door is red on the bottom side. And then we have to find out how to encode these things. And so I'm going to be having now a sequence of vectors, x at instance 1, 2, and so on, until capital M. And now we have that these x's are going to be simply a column vector of a specific matrix that we call it embedding matrix. So my embedding matrix might be a matrix of size, I don't know, 32 by 10,000. Every single time you multiply these 32 by 10,000 by a one-hot vector, you basically extract the specific column of that matrix, or you simply just apply a lookup table. Anyway, we just have a full small vector representing one word. Okay, so what next? We're going to be feeding these full dense vectors to my encoder, which was initialized with this first initial hidden representation. It goes inside and yada, yada, yada. We saw that before. And then this one outputs my hidden representation at the M index, the last hidden representation. Now, my X still keeps going. So now my next item is going to be the beginning of the next sentence. And then I'm going to be having la puerta de entrada es roja. And then this also is going to be embedded possibly with a different embedding matrix, since we are going to use a different language. And therefore, we have another embedding matrix, which is embedding my target sentence. And this is going to be fed to my decoder. And we have like the sequence, we still pass forward this hidden representation. And so, as you can see here, we start from an initial hidden representation. The hidden representation from initial location starts evolving, so we have basically a trajectory that we develop. Then we have this hidden representation at M, and then we keep moving it through a different set of models, and so we have, again, another trajectory that is moving around until we end up with the last word of the target sentence. Okay, so how do we train this system? Well, I have, for example, there my first target, which was la puerta de entrada es roja. And how do I encode these? And the end, actually. So the blue guys, my blue ball targets, blue ball Ys, which go from number 1 to n-1, are going to be the one-hot representation of my target sentence, starting from the second word onwards. So my target sentence starts from word number 2 until word capital N. Meanwhile, my input sentence in this side here was starting from T target 1 to n-1. As you can see, there is always a one hop between beginning, like between this one and the one following up. So here we have beginning. We force the beginning inside this item here, and then we're going to be forcing this guy here to output, well, what do we do? I wish this actually would work. Oh, it does work. Amazing. So this one outputs my first prediction, y tilde, and then I make sure the y tilde flies, well, it gets attached to my target through a spring. So it's going to be pulling that thing up. How does it pull? Well, you position all of those springs, the system is in tension, and then you do gradient descent to relax the system. You just go towards the minimum of the energy, right? So we have a very nice flat ending part. Anyway, so we do that for all of these, and so we have different white tildes, one white tilde for every target symbol, okay? And that's pretty much how translation used to work. We had an encoding, we had this final hidden representation, and then we start decoding things one by one, and then we force these outputs to be close to my desired target. How about the other language? I can use a different set of symbols. Again, we have this Qianmian, Shi, Hong, Si, De. This is entrance. This is entrance. This is door, like the doors from the pub. You can see, right? Like the yik, yik. This is to be, and this is red color of. Okay. All right, you do the same, and then in this case, you're going to have a different target. It's going to be, again, the one hot representation of the next word. So you start with beginning of the sentence, and the first symbol is going to be the entrance. And then you have entrance, door. Then you have is, door is, and so on, right? Is red color, and then of, and then end of sentence. Why do we have this end of sentence? Well, I need an end of sentence such that I can tell when my model is finished translating. And so once my model emits an end of sentence, done, okay, cool, I stop querying my system. How does the model know how to start? Well, we have 100% the same beginning for every translation system. So every time I have a beginning, the system knows, okay, I'm going to start with the beginning of the sentence. Once I'm done, E, stop, okay, end. Sweet. All right, so does it work? Yes, it works. Google used this stuff. Does it have problems? Yes. That's why Google stopped using this stuff. All right, so limitation for machine translation. So nearby context bias, what does it mean? So H of M is going to be more likely to predict and to encode information about the latest tokens, the latest symbols that we observe in the input sentence than the beginning one. Then we have another problem. Okay, first one, fine. We can actually find an alternative to the first part. So we said that the HM just mostly encodes the end. So how about I flip the sentence? Why not? We can do that, right? So I can do something that is like this. I have my sentence fed in the first recurrent network in one direction, and it's going to be fed in the opposite direction to another recurrent network, and then I concatenate those representations. So now the representation know about the information from both sides. But guess what? In the translation part, you cannot really do that, right? In the actual foreign, in the target language space. Okay, so let's get back to our issues with the translation. So first of all, yeah, there was the bias. Second one, fixed context size. This is actually annoying. The point is that if I have a sentence that is short, or a sentence that is like super long, the concept vector is still a finite amount of, like a finite vector. And so the vector cannot possibly encode infinite information. So the more you elongate the sentence, the more you're going to be running out, the sooner you're going to run out of space in that specific vector. Then you make the vector super long, but then you're going to be very inefficient for the other parts. So that's another problem, okay? This hidden representation is fixed. All right, that's it. And then that's actually, that's the major problem, the slow sequential data processing. Since we have a for loop, you cannot really parallelize the for loop because the next prediction depends on the previous hidden representation. The next prediction depends on the previous. It's a dependency graph that you actually have to go through, and you cannot possibly unroll it and process everything in parallel, right? So that's actually, I would say, the major limitation. That's why, again, people say, oh, we don't use recurrent networks anymore. No, not true. When I do control with a model, predictive control, that's what I'm doing, so it's bullshit anyway. Anyway, Parallelism. So how can we fix, oh, okay, this is pretty. So I made these slides for my undergraduate students. You're not my undergraduate students, but I will go through this slide anyway. Because you don't know how many times I had people telling me, wow, for real? I'm like, yes. So this is a matrix multiplication. Okay, what does it mean? I don't know. So let's go next slide. So I mean, it's kind of scary. Sometimes you see a table. Like, what is a matrix? A table. And then that's it. No, wait, is there more to that? Yes, there is more. Right? Let me go on. So let me give you these 3 interpretations of matrix vector multiplication. The first one is going to be the following. I can think about my matrix as being built by multiple rows. I have A1, A2, and yada, 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 until the mth row. And I multiply that by a single column vector, x. So we can think having these row vectors of n elements. And therefore, when you multiply your matrix by a vector, you just do the inner product between the first A and the x over there. Second A and the second x, the same x. The last A with the same x. And so at each location in this final vector, you're going to just compute. You're just basically checking what is the alignment between these vectors. What does the inner product measures? Somehow something cosine of the angle, right? So we have the cosine of the angle multiplied by the 2 norms. We don't care about the norms. We just mostly care about the alignment. So whenever I see this type of representation, I think about, oh, I'm doing pattern matching. I'm checking whether I check what is the projection of my input x towards those different A directions, okay? So this is my first way of thinking about matrix vector multiplication. Why is this relevant? Because the next slide I'm going to be using 3 different ways of thinking about these linear operations, and if you don't have them very fresh in your mind, you will not make, nothing will make any sense. So just try to be with me for this bit with this notation. And so this is going to be the inner product of a row and x. Second one, this one most of you don't know, but you should, but now you know, you will know for sure. So my A can also be thought as being a collection of different column vectors. And then I multiply that by a vector. How does that work? That's actually the definition of matrix vector multiplication. So this means, okay, those are vectors of m elements, and I have n of them. A vector matrix multiplication is simply the sum of all those columns scaled by the components in this item here. So how many components does this have? It has as many components as those column vectors. Because of, again, matrix vector multiplication is just the sum of the columns that have been scaled by that x. If x is going to be just a uniform vector of 1 over n, what operation are we doing? I just repeat the question such that you can answer correctly. If x is going to be just a vector, the one vector, the vector of all ones, and I multiply that by 1 over n, okay? N like Nancy. What operation is this? You have to shout. Average, right? Just one lady answer. What happened with the other boys, I don't know. But anyway, so this is just average, okay? So if all the x's are the same and 1 over n, just take the average of things. What if all x's are 0 and only 1 is equal to 1? So I have a one hot vector. What does it come out of this expression? You just select the specific column. That's what we've done before with the embedding matrix. So now you actually can reason about, you can figure out why matrix one hot vector multiplication is just a vector extraction, column extraction, because it's here. That's the correct definition, right? I mean, it's the more workable definition. If you like this stuff, check out Gilbert Strang textbooks or videos on YouTube. All right, he's a fellow YouTuber. Finally, okay, so this is weighted sum of the columns. Finally, there is this stuff. Some of you complain in my courses, but for me it's a third one. Maybe I'm whatever, my opinionated, but I am. So this is going to be a linear transformation of n-dimensional space X onto an M space. I usually refer to this as rotation. When you perform a a matrix, a linear transformation of 2D points with a 2x2 matrix, what are the type of transformation linear transformation you can apply to points in the two-dimensional space? You can do rotation, right? You can do reflection when the determinant is negative. You can do shearing. Then you can do scaling, but how do you scale? With scalars. That's why scalars are called scalars, right? But anyway, so those are, again, for me, a third way of looking at stuff, which is similar to the things I showed you just at the beginning of the class when we saw those transformations. Those were actually linear transformations with the nonlinearity on top. So I usually visualize a lot my things. Anyway, attentional sequence-to-sequence model, and then just attention. So attention allows us to perform context-based summarization. It basically, so if you have a recurrent network without attention, you just have the hidden representation is depending on this, whatever model, we call it decoder of the previous hidden representation and the current input. If I have an attention, I can just stack onto my input also another input. So I have a new input, C, which is my context. Where is that context coming from? Well, that's a context-based summary. That's why it's called C. Okay, interesting. So first one, what is this stuff? We need one more, okay. So this is going to be, S was my source sentence. This is going to be a sequence of words in English. The front door is red. Then I send them inside my encoder. Now I have a bunch of columns, which are the corresponding columns of my embedding matrix corresponding to the words I said. Because these can be thought as being one hot, you multiply by the matrix, you know. Very good, so this is my S. It has all the words in my sentence. Now I take my S, I flip it, and I multiply by a single column vector. What I do here, I check the alignment of my hidden representation at the previous state against all the embeddings I have, okay? So this is gonna be R, just the scores of alignment, if you want, between my previous hidden representation and all my word embeddings. Cool. Now I have my C, my context, is going to be this SA. What is that stuff? So let me show you. First, A is gonna be the soft argmax. Again, many of you might recognize this if you remove this word, but it's incorrect. So you have the soft argmax, which is returning a probability distribution out of this dense vector. So now these A's are numbers between 0 and 1, they sum to 1, so like a probability, pseudo probability. And now I have this thing here. What is this? I use now the previous definition, the bottom right-hand side. Remember, SA, it was the weighted average. Now A is actually probability. You actually have like a sort of expectation if you want, right? And so you just have an average of the embedding vectors based on these attentional weights. I call them weights. But they are computed. And so these are fast weights. What does it mean? So fast weights are weights that are computed at inference time. And that's why they are fast, because they change at every single inference. Meanwhile, the other weights, the slow weights, are the ones that change very slowly by gradient descent. So gradient descent changes slow weights. Fast weights are changed by inference. And so we have two types of weights. Interesting, cool. All right, sweet. So what's next? Attention has no weights. Well, we call them fast weights, but again, there are no weights. It's just computed at inference time through just computations. And then it supports variable length source and target. Why is the case? We never care about how many of these, what is M, right? M can be any number. Therefore, R is going to be a m-dimensional vector. It doesn't matter what M is. Therefore, the A is going to be, again, an m-dimensional probability distribution, which is going to be weighting the m number of things. So everything just cancels out. You just have a context that is independent of the actual length. Cool, cool, cool. So how visualization of this stuff? We have my input sentence that is being fed into the encoder. Then we're going to be sending the final hidden representation to my target. So I have to my target, to the decoding system. So I have first the first part of the sentence, la puerta de entrada es roja, and the other, on the top right, we have the second word on words, la puerta, etc. And so here we have this decoding part, but then I'm going to be checking on every single of these input embeddings, or whatever source vectors, what is their projections. I send them through a soft argmax, and I see that to actually be able to predict the first la, I really should pay attention to the first token, which is the one that is actually looking at the of the sentence in English. Then so that's going to be my first A1. Then I do the same for the second part. I'm going to be seeing that I have to make all these other connections. So again, I compute all these projections, and I'm going to be seeing that for coming up with puerta, I just look at the door. But then you don't have the de in the English. So in this model just looks both at front door together. In Spanish, you require the de. So since you say front door, then the system will look at these two words for 3 times. That's why you have puerta looks at puerta, de looks at both for the attribution, and then entrada actually looks at the front part. All right, so let's actually see how self-attention works. We're going to be having here a set of x's. Right now, I'm not even having more sequences. Before we were talking about sequences. Now I'm talking about just set of vectors. So I have this set of vectors, capital M vectors. I can stack all of them together, and I have this capital X matrix, if you want. So I have my X there, one of those vectors of my set, and then here I have the entire set. So this is my big X. So one of these, I actually took it out as well here to just, I draw it again. For just this X here, I compute a question, Q. And so a question, Q is going to be just a rotation of my X, specific X. So I send my X through this linear transformation. So that's the rotation. And this is my Q. I have a question. How to make parmigiana? You know how to cook? Well, maybe. So that's my question, right? How to make parmigiana. And now I have to do something. I'm going to be computing my K as a rotation of my X's. And I do this for all of these X's. So if I have a rotation of the single X, I have a single K. If I press Shift, you're going to be having the capital X, you have the capital K. This is just the concatenation of those small X's. This is going to be just the concatenation of these Ks, right? This is just basic machinery, right? All right, so I do that, and I apply this transformation to all of these. So this is what my friend calls it a convolution, but there is no convolution, but, well, it's a convolution. And that's my K. So K is going to be the collection of all these keys. So I have my question, how to make parmigiana, and then I check. Well, I don't check yet. That's coming next slide, next formula. Actually, first of all, I also do another rotation. I rotate my X's with this W matrix. And I have all those V's. All those V's, I can make the shift. I have a bunch of V's as well now. One V for every X. And now I have this final V there. So okay, there you go. We are going to be trying to see this first match. This is going to be similar to the previous match. I take the K, I flip it, and I multiply it by the single Q. So I check all the projections of my single Q against all the Ks. What does it mean? So Q is going to be how to make parmigiana. And these Ks are going to be all the titles of the recipes I can do, many. But some of them are going to be chicken parmigiana, and the other one is actually the true parmigiana, which is the eggplant lasagna thing. So if I do this multiplication, most of them are going to be orthogonal, fish, stew, something, something. 2 of them will have a non-zero type of projection. Sweet. So I do that projection. I send it through a soft argmax. I get the probability vector. This is my transpose of the K. I multiply, get this soft argmax. I get this A vector of probabilities. And now I just use these vector probabilities to make a weighted sum of these V's. What are the V's? V's are going to be the content of the recipes. So if Q was the question, what to cook tonight, and K is going to be the list of all the titles I have in my recipe book, then V is going to be the content of all the different recipes. So what does this do? Unfortunately, it's going to be just mixing the two recipes, the one for the chicken parmigiana and the one with the eggplant. Maybe we don't want to do that. We can change the mixing factor by making the system cooler, so you lower the temperature. This is going to be just an argmax. So now you just extract a single value. But usually you don't need to do that. You just use soft argmax instead. Sweet. So finally I have my context. Now interesting is that this context doesn't change if I change the order of any of these vectors. And so you can see that C is going to be invariant to permutation of my input. So my input, I perform any permutation of these V's is going to be the same permutation of these V's. Therefore, the A's also get the same permutation. This system is completely permutation invariant. But then I'm going to have how many C's? I'm going to have here, I can plug here the whole X. And so there I'm going to have as many C's as I have X's. Now if I change the order of this item below, I will automatically change the order of the C. And so if I have many C's, 1 C per every input X, I will have a system that is permutation equivariant. The same permutation down, same permutation C up on the C level. The single C instead is permutation invariant because it doesn't care about the order. And so the last thing I wanted to show you, so this is called self-attention. You can do cross-attention by replacing the X with a Y here and over there. So now we have a system to encode vectors, set of vectors. How to encode sequences, which are sets with order. Well, that's the only last part. I want to show it to you. So from sets to sequence, pretty straightforward, actually. So self-attention is defined over sets of vector, that everything I talk about doesn't have order, and everything is actually computed at the same time. You can completely parallelize the whole thing. As you see, I just press shift, everything went capital, boom, single matrix multiplication done. So a sequence can be cast to an augmented set by adding to the input representation information about the index position. And so as soon as you add to my X, which is going to be the representation at the index M, also some encoded version of my location, now my set will have a representation which not only reflects the content of the word, like the specific word you're looking at, but also will reflect the index you're looking at, okay? And so in this way, you can use a set encoder to encode sequences. But guess what? Set encoders are kind of the most loose type of encoders we have. And we can encode every possible type of data by adding more information. So let's say you have a molecule or a protein, and then you have these different amino acids, but then you also may have a 3D structure. So what kind of network would you use to encode the 3D geometry of a protein? Well, you can just use a set encoding for the different items where you add to each item information about the geometry, okay? There are different ways to do that, but it turns out that this transformer, well, we didn't talk about the transformer, we just talked about the technology behind the transformer, which is this attention. It's a super powerful mechanism because it's the most loose type of encoding we have, which is set encoding, which you can always enhance with specific changes, okay? So that was pretty much my talk for today. In case you want to hear more, just ask questions and I can tailor to you more lessons, okay?
Hi. So thank you so much for the fantastic talk. So we have a bit of time for a couple of questions from the audience.
My name is Deborah. I'm an undergrad student in Brazil. And this is the first time that I heard the the energy being talked about like a spring.
Oh, okay.
And I really, I have trouble understanding stuff, and I think it's really fascinating that you showed like different ways to explain something that I've seen a lot in my lessons, but this is the first time that I've seen in like a spring form. So can you talk about more how you came to this metaphor of the springs?
Right. So thanks for the question. So maybe I'm not the smartest around, so I always try to make things simpler for me. I spend so much time to understand things, and that's like how you basically acquire some maybe knowledge. It's been 16 semesters I've been teaching all this stuff forever, so I know this stuff in my dreams, I didn't have to prepare. I can just talk about whatever you want. I'm a teacher, so I love teaching. Math, science, cooking, dancing, music, and I always try to make things the simplest I can, but not simpler. So you should be able to, I usually use my mom as a guinea pig for my explanations. If they lasted less than 15 minutes, she keeps awake, unless otherwise it doesn't really work. But anyway, the point is that if she can understand, then you likely also will be able to understand. But also I teach in primary school. So my youngest kids are 8 years old, and I teach the same slides. I don't use the math, but I just show the bubbles. I also use my aunt, and she's old, but I still show the pictures and the bubbles and the things. She's like, oh, this stuff you teach in school? I'm like, yeah. And they don't get it? Like, no. Do they listen? So, but again, so I use two techniques. One of these techniques is called guided discovery, where I take you by hand until the door, but then you had to step. Usually I just help you, but I don't step for you. And so whenever you understand, you are the one acting. You are the one gaining the knowledge. It's not that I'm going to give you something, because you're not going to be obtaining that. You have to be able to make that click in your mind yourself, right? And so I always just try to give you as much as I can, but you have to make that extra step. And so this, again, it's called guided discovery, where you are driving my lessons. Mostly also with my undergraduates, I do Blackboard lessons only. I don't have slides. And then Blackboard starts black. And I have no idea how it's going to be ending up, the Blackboard. And I'm like, okay, what do we do today? So we start, okay, I have a rough idea where we are heading towards, but I'm just asking them to tell me how to move forward. Then I only select the answer that I like and they match my path, but I pretend as if they were in the driving seat. I do the same with my middle schoolers, 10, 11 years old. I went there for teaching 1 hour of class. They kept me there for 4 hours. And they were they kept asking questions and asking, and I kept answering. And they're like, you know everything. Like, not everything, but those questions about technology is like pretty okay. Oh, our professor don't know shit. Like, that was my favorite professor from middle school. But anyway, the point is that that's the second point. So the education should be a playground, like the class should be a playground. You should have fun, because when you have fun, you actually make memories. You can make memories two ways. Either you're going to be, let's say, not facing nice situations, or you actually have very nice situations. But only with emotions you actually make memory, right? And so what I'm trying to do is going to be having you have a good time. I'm having the best time of my life. I get even paid for doing this. You guys, it's a very nice job I have. And moreover, if you want to know more about this, I have a textbook. Check out my website, check my Twitter. So there are many here of you. I'm pretty annoying on Twitter. Like, I'm pretty vocal. You can find me under Alf, A-L-F, C-N-Z, like my surname. 3 letters. I put all my educational material online. I really love teaching. I really love what I'm doing. So I guess, yeah, you can see.
Thank you.
Sure.
That was a good answer. So we'll do one last question. Anyone?
Now it's going to be the technical question.
Hi, thanks for the talk. And you mentioned briefly control applications.
Yes.
So have you been researching attention in real-time control like microseconds?
Say again, sorry?
Have you been researching real-time control attention by like microseconds?
So I was mentioning before control because it's the same circuit of the recurrent network where I change the future predictions by changing the current input. So that was my connections. In the second part of my semester, we have like 3-4 weeks of optimal control, figuring out how to change the output given that you change the input, the input configurations. And that's basically just using the same circuit that the recurrent network I showed you before does. And so the point is that my courses, my classes are giving you just the basic knowledge that you can apply for different things. I don't know what you asked in your question about my microseconds attention thing.
Like my research is on dynamic control in real time.
Okay, I see.
So in electronics. So I have been trying to replace like a model predictive control with neural networks. And attention, I think it's a very good tool, but it's very expensive, like computationally. So my question is, how is your view on applying this technique in real-time control?
That's a very good question. If I knew, I would have written about it. So I don't do research, I do just education, but we can take this offline. We can definitely see what are possibilities to move forward there, okay?
Thanks.
All right, so Enzo will now bring some good news for you in a second. Please do check Alfredo's YouTube channel, it's absolutely amazing. I have to say though, the 3D version is kind of better, but he's gonna be here all week, you'll be able to catch him around. Let's thank Alfredo again.
Okay. Why it's not showing? Where is the? Okay. Hey everyone. So some housekeeping here, a couple of updates. We added 30 minutes more to the program, like to the break now. So you know that now there is a poster session coming, there is lunch. So we modified a little bit the program now. So we will resume at 14:30, at 2:30 p.m., okay? Not at 2 p.m. as we were planning before. That's first comment. So you will have more time to go for lunch, and please check the posters around because I think they are really, really cool things. Remember that any changes to the program are going to be posted online in the website. So I don't know if you have checked, but the program is there, okay? So you go, there is a kind of Google Calendar thing that we keep on updating all the time in case there are changes. If you click on the names, on the titles, you have more details, like speakers, where their affiliation, or where the event is going to happen, so do that. Also, please be aware of your personal belongings. That's important, okay? We will lock this room. So if you want to leave something here, it's up to you. This will be locked, but then when we unlock it, people are going to come in all at the same time, so I'm not sure about it. So keep stuff with you. Also, regarding the poster competition, so we have set a set of juries. So there will be juries going around. You don't know who they are. They are faculties. That's the only thing I'm going to say. So you will explain to everyone your poster, but some of them are going to be evaluating you for the competition, okay? The best 2 posters will receive the KHIPU Best Poster Award, which this year will consist on a paid trip, hotel, and flight to New Rips 2025, okay? So just make an effort there. And this is gently sponsored by the Latinx in AI that you can also find in the booth in case you want to go and say thanks. Okay, great. What else? Social media. We are using the hashtag KHIPU2025, so please post the stuff on social media in any network you want, like X, Instagram, LinkedIn, and now Blue Sky as well, and tag us there. You can use the Add Yours template on Instagram. Okay, I don't know what's that, but it's something. Okay. Remember that we have a WhatsApp community. This is important. If you scan this code, it will take you to the WhatsApp community. You will see that there are different groups. The most important from our side is the announcements channel, okay? Because we will be posting everything on the announcements channel. So don't tell afterwards that we didn't tell you, because everything is going to be there. Good. And use your Mac. We gave you a Mac with your thing there, with your bag, so you can use it in the coffee break, then you wash it, and then you use it again, so we don't spend a lot of plastic there. Okay? Well, I think that's all. So we are coming back 2:30 p.m. Enjoy the lunch. Lunch is going to be served. Where is Jocelyn? Just outside here. And lunch boxes, okay. And there are some seatings around, so you find your way. And then be at the poster session, especially people who has to present today, and everyone go there to ask questions. What else? Wait. Okay, please don't post the link of the WhatsApp community online or anything. It's just for us here, okay? Because otherwise there will be some. No.
Oye, ¿y esto? Un paso slide, no sé de quién es.
Test, test.
So I know it's hard to be back from lunch and posters. Posters were really interesting. But we are about to start here, so please find your spots. Thank you. So it is my great pleasure to introduce Isabel Austian. Isabel, with her collaborators, they are shaping the future of natural language processing. She's a professor at the University of Copenhagen, where she leads the Natural Language Understanding Research Group. She's passionate about building fair and accountable AI. Her research tackles some of the most pressing challenges nowadays in the field: explainability, factuality, and bias detection. Her journey spans top institutions. She was a postdoctoral researcher at University College London and earned her PhD from the University of Sheffield. In October 2022, she made history as Denmark's youngest ever female full professor. Currently, she leads the ERC Starting Grant, an explainable and robust automatic fact-checking. Beyond research, she's an influential voice in the NLP community, serving as president of SIGDAT. SIGDAT is the organization behind EMNLP conference. EMNLP is the largest NLP conference in the world, and it will be in China for the first time this year.
Thank you so much for the kind introduction. Now, I just really hope that the talk can live up to these expectations you must have built during the presentation of my bio. So I'm very happy to be here today. I've been asked to give a presentation on natural language processing fundamentals. Now, there are so many different ways in which one can give an introduction to my field of natural language processing. And I just hope that I've managed to somewhat get an idea of what your background might be and what you might be interested in. I'll be explaining a little bit of everything, hopefully providing a good primer for some of the other talks and practicals later on in the conference. So the first question I thought some of you might have is, what is NLP? Maybe not, but anyway, I thought it's a good place to start. So what is NLP? NLP is about building some kind of computer systems to try to understand, process, and also generate natural language. It's about getting a deep understanding of language, not just about some surface level processing. And this means development of some tasks, methods, and data sets, including evaluation methods. Historically, it's a discipline that has developed from linguistics, and it's moved more and more into computer science over the years. There are many different ways, many different tasks people are working on, and this here on the right is what ChatGPT said NLP tasks are, so you can have a look there. You see things like name entity recognition, language modeling, speech recognition, and so forth. All right, now when I took my first NLP course, this was one of the core things that we were taught. Why is NLP so hard? So I thought I would also share this with you today. The reason it's so hard is that language is really, really complicated. When you look at language, the way language is composed, then you can think of it as this natural language processing pyramid, where you have really basic tasks at the bottom and then more complicated tasks at the top. So on the bottom, you have morphology, you have how words are composed of different syllables. You have syntax, trying to understand grammar. You have semantics, the meaning of text. and you have pragmatics, which is meaning in context. And at each of these layers of the pyramid, you have different kinds of ambiguities, different ways in which things can be understood. And they all build on one another. And when you then look at the tasks which require pragmatic understanding, you still, in addition, have to deal with all of these other ambiguities further down in the pyramid. Now, another kind of traditional example that some of you might have heard of are garden path sentences. So garden path sentences are sentences that, upon first reading, you might understand differently, or you would understand differently than upon the second or third reading. They lead you down a wrong path. So here, I can read some of them out. The horse raced past the barn fell. What does this mean? It means the horse was racing past the barn, is maybe how you would read it. But it means the horse that was raced past the barn fell down. And many more here. The man who hunts ducks out on weekends. You think maybe it's about the man who hunts ducks, but it's the man who hunts ducks out on weekends. So many more examples here. And of course, there are examples you wouldn't encounter every day, but they do occur. And they're a good example of why language is so hard for machines to understand. Then you might think I'm just bringing up these linguistics examples, and they're not actually all that relevant. But ambiguities are a real problem for downstream tasks. And here is an example table I've pulled up from a recent machine translation paper where they look at different kinds of ambiguities and how they really impact machine translation. So you have some ambiguities like Jane saw the man with a telescope. Then you don't really know if Jane saw the man who was holding a telescope, or if she saw the man through a telescope, for example. And there are many more examples like that. And in order for machine translation systems to work, these ambiguities need to be resolved in one way or another. Okay, now the next thing. I hope that some of you were there this morning too and were paying attention. If so, this slide seems very familiar. And I promise I did not steal this slide. We both came up with the same idea independently. Nevertheless, let me give you a brief introduction of the history of NLP. Not just AI, not AI more broadly, but NLP more specifically. So I think the beginnings were kind of the same as for AI more broadly. There was information entropy was a very important concept in the early days, and also the Turing test. And then there was some early work on machine translation on translation. So that was in the 1940s. Then between the 1950s and the 1990s, NLP developed very, very slowly. I would say there were the beginnings of NLP. There was some developments in linguistics, so the Chomsky hierarchy of grammar. There were hidden Markov models, which were used quite frequently for NLP tools. Then there was the Brown corpus, which was a large collection of text that was used to extract some statistics for later usage. And then there was ELIZA, the dialogue system, and there was early work on syntactic and semantic parsing. Then between the 1990s and the 2000s, NLP really took off as a field. There was a lot of work on statistical NLP, machine translation, parsing, and so on really took off then. And people applied all kinds of different machine learning methods, SVMs, CRFs, logistic regression, and more to NLP, and did some feature engineering and so on. Then came the era of deep learning, and you already heard about this morning. So you heard about the distributional hypothesis and about word embeddings a little bit, and about RNN-based approaches, which were very, very popular. And then afterwards, sentence embeddings were developed. Some of the sentence embeddings, the earlier ones, were based on RNNs as well. Then from 2020 onwards, language models really took off as the predominant approach. And from there, we have different kind of probing methods, instruction, tuning methods, and also conversational interfaces. So that was a very brief history. So now, with that out of the way, let me get into some of the recent methodological developments. So in terms of that, I will go into language modeling, into in-context learning, human preference alignment. Then I will give you some impressions of some of the recent tasks and challenges. This is by no means exhaustive. It's partly my own selection bias, things I find interesting. And then at the end, I will try to tell you that even though there is already there is so much work going on in NLP, there are still many open tasks, and I will try to give you an impression of some of the open research challenges you could work on if you're struggling to find a research topic as a master's or PhD student, perhaps. All right, so recent developments. I'm sure you all know that generative AI has taken the world by storm. When ChatGPT was released in November 2022, people took to social media and posted all of their funniest interactions. There was someone who was trying to get a ChatGPT to condemn itself in the style of Shakespeare. People were using it for programming tasks and also for things like trying to make money, trying to get investment advice. And this meant that ChatGPT really rose in popularity, and in terms of daily users, it was almost up there with Amazon and WhatsApp. Now, one question you might ask yourself if you're not working on NLP is, how does this actually work? Well, these large language models, they're under the hood basically just complicated versions of ordinary language models which have been around for decades. And language models, they calculate the probability of a sequence of words. So you have some kind of prompt, some kind of beginning of a sentence, like I saw A, and the question is, what is the most likely next word? Maybe it's cat, maybe it's not. But then when you have the next word, you could again ask, what's the next most likely word, and so on. And you could also, given a sequence, calculate how likely the sequence is, and compare if it's more likely or less likely than another sequence. Right. So with language models, you sample iteratively one word at a time, and given a prompt or its generated history, a language models predict the next most likely word. It's as simple as that. And there have been many applications of that over the years. Some of the earlier ones maybe search engines where you get you type in something and it will show you some potential completions of that. Right, now for language models, I also want to tell you a little bit about how they developed. So language models have been around for a long time. They've not been developed by OpenAI, but they've been around since the 1980s. There were n-gram language models that was still pre-deep learning, so that was manual feature engineering. People were thinking about what is a good context window. Is it 1 gram, 2 gram, 3 gram? There were all kinds of tweaks regarding how do you estimate these probabilities. Right. Then neural language models came around in 2020. Then we had these transformer-based language models. Now we've not had a proper introduction to transformers today, but they're based on attention, and we did hear about attention earlier today, so maybe someone else will fill you in on the exact somehow technicals behind transformers, technicalities. And then we had these pre-trained language models, including BERT. Then prompt-based learning came around, and finally these conversational interfaces. All right. So now I will give you a very brief, high-level overview of prompt-based learning. So to explain prompt-based learning, I will just give you a brief recap of in-weight learning, traditional supervised learning, which you heard about this morning. So in traditional supervised learning, you have some kind of input, which can be a sentence, and then you have an encoder, which transforms the input to some features, and then you have a classification head, which says says if the input assigns the input to some kind of label, helps to transform the features to some sort of label. And in sentiment analysis, maybe it's 0 or 1 or -1, 0, 1 or such. So that's that. And you have a test set, and there you can do it for unseen examples, right? And basically, you want to you need some kind of way of learning that. You have some kind of weight updates based on gradients with respect to a loss function. We've seen this before this morning, and you tune these using the examples you've given. Now, with in-context learning, it's in some way, it's much simpler because you don't have any updates, you have no grades, you have gradients, you have no loss functions. You just have the model that's already trained, the language model, and you have these data samples, and you directly pass them to the model. And the model is frozen here at the time of application. So somehow you have this input. It can, for example, be the sentiment examples, some previous examples, and you pass it a new example at the end, saying good meal, sentiment, and then you expect it to just understand that it should output the sentiment. Right. So it's all just language modeling. It's usually autoregressive language models that are used, already sort of explained language modeling. And so you normally pass these kind of examples as part of the context. So here it would be the smell of fresh grass is the best, positive, I can't stand fish, negative, blah, blah, I love my new watch, and then you would expect a positive to pop out. But there is no indication that the model should actually do that. So it just picks up on that from the context, but in theory it could put out anything. It doesn't have to put that out. It's just the most logical thing for the model to do, the most likely thing for the model to do based on the examples it's seen before. And you can also use this to prompt for all kinds of knowledge. Yes, and so because when you have the input you provided with these kinds of examples, it gets some knowledge about the task, or can infer some kind of knowledge about the task and can understand what it's supposed to do because it's seen these things, these examples at training time. Now, there are different kinds of input formats you can use. Usually you have some kind of instances here, and then when you want to do classification, you have some kind of verbalizers, positive, negative, neutral. It doesn't have to be that. It can be also, it can also be yes, no, maybe. You decide and you try what works best. But they're manually defined by the user. And then the outputs are generated and parsed. So the outputs here, it can be positive, it can be that the model outputs positive, but it can also be that the model doesn't actually cooperate. It can, you can have a positive, negative as prior context. And then if you type in, I love my new watch, arrow, it can maybe output, it's the best one I ever had. So it doesn't need to follow the instructions. You can also try to get it to output some kind of class ranking with probabilities, but it's not with every API that you can actually do that. So it works better if you have an open source model. Right, and you can also deal with text generation tasks in this kind of in-context learning setup, for example, grammatical error correction. Right, so the advantages is instead of just training a sentiment analysis model or a part of speech tagging model or a syntactic parsing model, you now have one model that can, in theory, perform all the tasks. Not necessarily very well, but it can at least perform all the tasks, and you don't need to do any kind of expensive retraining. So that's a real positive. But also it doesn't always work. And yes, second. Okay. So you can use the models with examples, or you can use them without any examples too. And there are also very different ways of phrasing the instructions. So here you can, for example, say, correct the grammar of the sentence, I loves my new watch. Or you can say, translate to French, I love my new watch. Or you can say, determine the sentiment of the sentence, I love my new watch. Many different ways in which instructions can be provided. Also, one thing that makes a big difference is how many different examples you provide to the model. So either you provide no instructions, no previous examples, or you can also provide multiple. So you have maybe one shot or few shot examples here of how to address the task. The more examples you provide as context, the better the model performs. This is just for 0 shot, 1 shot, and few shot, and it's done with GPT-3. So you can see that the model performs quite a lot better when you have more examples provided as part of the context, and then it also outperforms fine-tuned BERT model and gets closer and closer to human performance. Right, then I've already mentioned a few times that the model doesn't always cooperate, it doesn't necessarily do what the user wants it to do, and the reason is that it wasn't explicitly told what the user wants. So in order for the model to understand what the user wants, it needs to actually be fine-tuned in some way. And the way it's fine-tuned is with some human preference data. So this is called human preference alignment, and there are 2 commonly used methods. There are many more, but yeah, there is reinforcement learning from human feedback, and there is direct preference optimization. For both of these kinds of methods, what is needed is some kind of human preference data here. So when you have a prompt such as write me a poem about the history of jazz, then you need different generations from the language model, and then different judgments by humans saying which of the generations they prefer. Sometimes it's done pairwise, sometimes there are multiple examples. It depends on the exact setup. And basically the difference between these two is that one of them uses reinforcement learning, the other one just uses maximum likelihood estimation and doesn't do reinforcement learning. So this one is nowadays used more often. I think it's leaner in terms of how it's trained. All right. That brings me to the part about recent tasks and challenges. Let me just see how I'm doing for time. How am I doing for time? Good? Okay. All right, I think I have half an hour left. All right, recent tasks and challenges. So maybe I can talk a bit more slowly. So here are some handpicked recent tasks and challenges that I think are interesting. And I will go through them one by one, just providing some kind of intuition of what the current research in that area looks like. So one thing following up from the previous introduction is these language models are so powerful, they can do all kinds of things, they can be applied to all kinds of tasks. Seems a bit like magic, or seemed a bit like magic. So does that mean we're seeing kind of a development of artificial general intelligence? And my answer would be no. That's not what's happening. What we're seeing is models that are very, very good at multitasking, but they also have many inherent limitations. And there are nowadays many papers that have looked into what the limitations are. This one was one of the earlier papers published in 2023 that's looked into different aspects. So yeah, they found, for example, that in terms of benchmark performance, the models outperform previous models on many benchmarks, but this is also due to dataset contamination because they've seen the test datasets as part of their training, and so they're not actually doing holdout evaluation, then they're cheating because they've seen the answers already. They're just remembering the answers. And there's much recent work showing that that's actually happening, trying to recover the original training samples or test samples. Yeah. Another thing is that LLMs, even though they're doing so well and they're also doing well on multiple languages, they're still not doing so well on low resource and very low resource languages. In terms of reasoning, it's kind of a mixed bag. They're okay at they're okay at temporal reasoning. They're not so good at the other kinds of reasoning, like multi-hop reasoning, spatial reasoning, and mathematical reasoning. They also have many hallucinations, meaning they produce things that are factually incorrect. And the takeaway from there is that, well, ChatGPT is a very good multitask learning model, but it's not some kind of AGI model. And even though there are more recent models now, that fact still holds. There are still, these issues still persist, even though they have to some degree been mitigated. All right, so of course when ChatGPT was released, one of the first things my PhD students did was to ask it who I am, their supervisor, and got this long kind of text, which I still think is kind of funny to a fun way of illustrating the factual inaccuracies. So it starts off by saying I'm a researcher and academic and so on. It gets that part right, but then it gets my PhD year wrong and my title. The areas of research are sort of a mixed bag. Then it says I've published numerous papers at top-tier conferences. It's hard to argue with that fact. Yes, and then it makes up some award that does exist, but I never received, and it wasn't even awarded to anyone in that year. So, yeah. Also, some kind of editorial board duty. I'm not doing that. So anyway, well, this was by the previous version of ChatGPT. If you ask it now, it will provide something different. But anyway. Yes, so there are many kind of factuality challenges of large language models. They provide this kind of, they produce text that seems really fluent and has this kind of authoritative tone, and it seems correct, but then if you inspect it more closely, you will see that many things are plausible but made up. So this is an issue. It's an issue in terms of misinformation spreading online. And it's an issue because large language models can be accessed so easily, which means that misinformation is spread more easily. And there's also this issue of general information contamination, information on the web becoming less and less reliable. And that's also because people perceive LLMs still to be a knowledge base. They don't just use it for creating email templates and so on, but also for some kind of factual information inquiries. And the fact that the evaluation of language models is still a bit shaky. It's LLMs being used to evaluate LLMs is kind of a very common approach, this LLM as a judge, and that doesn't make it any better, right? So, right. There are many ways to address these kinds of threats. There are things that go beyond just the technical challenges. So, of course, education is very, very important in that, and AI regulation. But that's not what I'm going to talk about now. Otherwise, I could be standing here for the whole rest of the day. But anyway, I'll just pinpoint two things that can be used to actually address this issue of factuality, and that's retrieval-augmented generation and also detecting and correcting factual mistakes at test time. So retrieval-augmented generation is a very common approach nowadays. And the idea is that, well, language models, they're by design, they only have the knowledge of the text they've been trained on. And so if you want to ask them about anything more recent, then they just won't have the background knowledge. That's why you need to retrieve some additional documents at test time when they're applied, and then they can use that additional context to generate a more accurate response. And so in its kind of most basic variant, you have the query here, and then the query is also passed to some kind of search engine, and then some additional relevant documents are retrieved. Then from these relevant documents, some kind of chunks are extracted, and they are passed on to the language model as part of the context, as part of the prompt. So you might ask, what's this one? How do you evaluate the fact that the OpenAI CEO, something dynamics? Not sure. I stole this image. Anyway, you have some kind of question. You append the context and then maybe say, take this context into account, and then produce the answer. Going a bit off topic here, but some of the recent research my PhD students have done, they found out that depending on how you phrase this, you get very different results. So if you just add the context, or if you say, you must take this context into account. So many different kind of options for how you can actually work with RAG, even just using simple variants. Okay, and then in addition to this kind of naive formulation of RAG, there are many more advanced versions of that. So not all documents are equally relevant, so you might want to do some kind of re-ranking of the documents, and then you might want to summarize the documents and then re-rank them, or extract some paragraphs and then re-rank them and then summarize them, or kind of some kind of combination of that. And then there are also modular architectures, which are quite complicated, where you do some kind of combination of retrieval, re-ranking, rewriting, and so on. Lots of different variants of RAG these days. All right, then we've also done some research on fact-checking of machine-generated content. The idea is that, well, this RAG it's nice, and you can do if you actually developing, if you actually want to work on developing language models, making them more usable. And it can work, but language models are still language models. They're not trained to be factually correct. So this is a real issue. So a more principled approach would be to actually fact-check the outputs, which is some of the work we've done. So you can have this kind of modular architecture there, where you have an LLM response. Not sure if the clicker is still working. You have this LLM response. You decompose it into sentences, into atomic claims. You then reformulate the sentences so that they make sense out of context. You identify check-worthy claims, so there are opinions, and then there are also claims in text. And then you retrieve some kind of evidence to verify these claims. You determine the stance of the evidence towards the claim. Does it confirm the claim, deny the claim, question the claim, and so on. Based on these, you determine if the claim needs to be corrected, and then you put it all together and edit the original text. That's quite an involved process. In our research, we've shown that all of for this step here, you need a search engine, and for everything else, you can just use an LLM. You can, in fact, use the same LLM, but it will perform a lot better than if you just, in terms of factuality, than if you just have the original output. So that's worth doing as well. Okay. Now, one thing I've alluded to several times is that depending on the prompt that you use, the answer will be quite different. And this is a real issue with LLMs, this fact that there is this instability depending on what kind of prompt you use. So this image here is from an article on multi-prompt LLM evaluation, and it shows a task here that's about homophone detection. And here you just have different ways of phrasing the same question. They're really just different ways. So please identify the homophone, or determine which of the words is a homophone, or so on. And here you can then see the result of that for the different prompts. So you have prompt 1, prompt 2, prompt 3, prompt 4. And the bars here are the different language models. And you can see that for the green one, it's Text Da Vinci for the green one. There is the least kind of amount of variation. But there are some language models, GPT 3.5 Turbo, which performs really well for some of the prompts, and really, really terribly on some of the other prompts. And so that's a real issue. And it's because, well, there are so many different ways of answering this, and the language models, they don't know how to do that. They've not been told maybe how to, they don't have any training data about the specific task, perhaps, or so, yeah, they are very brittle to these kinds of phrasings of the prompt. Okay. Now, this has led to a lot of work on prompt engineering, people trying to see which prompt works best. And more recently, people have also worked on automatic prompt tuning. So not just manually firing lots of prompts, but automatically generating some prompts, and then using other LLMs to evaluate if the new prompts are better than the old prompts, essentially, and then thereby updating the language models to be more stable. All right. Now, another issue is that the language models, they're opaque. It's difficult for people to understand what kind of knowledge they actually encode. So this has led to a lot of work on interpretability and explainability. And two streams I'd just like to highlight, you can see more on this slide, model understanding and decision understanding. So for model understanding, it's about getting an idea of the features that the whole model encodes. And then for decision understanding, it's about understanding how a model arrived at a specific decision. And both of these are very important for model development. So my group has done quite a bit of work on decision understanding, and I just wanted to highlight one thing that we've worked on the last year, and this is about feature attribution. So the idea is when you have a decision, you want to attribute it to specific features of the model. And there are two commonly used ways of going about this. One is to attribute it to specific neurons of the model. It's a very fine-grained view. Or to attribute it to specific instances, which is something that's easier for users to understand. And so in this work, we've tried to marry both of them so that you can first understand which instance is responsible or which instances are most responsible for the prediction, and then also the neurons within that. So, yes. Another issue with language models are that they often carry some kind of social biases, and this isn't exactly a new thing in NLP, but the older generations of models that we developed, they also had the same kind of problem. And the reason is that the training data that's used is in itself contains these kinds of biases, these harmful societal biases. But with language models, it's just more difficult to try to detect and correct them. And to do that, what can be done is to use some kind of interpretability methods. A common one is to use probing. And for that, the task is just to formulate some kind of probes and then see what the response by the language models is. And so some work we have done is to try to unify some of the research on biases in LLMs by proposing the social bias probing dataset, where you have some kind of category like religion or gender, and then you have some identity like Catholics or female or so on. And then you have a stereotype, for example. There's a wonderful one on this slide. Are all terrorists? So it can also be are all lazy or whatever else you want to put there. And then you can combine this all and pass it to the language model and then see what kind of probability it will assign to that. Or you can you can just combine the category and the identity and then see what conclusions it will have for the stereotype. Yes, so based on that, we proposed a dataset that can be used for social bias benchmarking. And I think I will skip this one. Another thing that's gained a lot of popularity recently is to look into what kinds of political biases you might see in language models. So the idea is that you have this kind of political compass where you have economic left, economic right, authoritarian and libertarian here at the bottom. And you want to place language models into this kind of grid, depending on what they're likely to produce, what kind of output they're likely to produce. And we've done that systematically for many different language models. And you can see that so this is for the mixed raw language model, and you can see there's some kind of variation depending on the specific prompt. Yes. So, what else do we have? Okay. So debiasing language models. You might then also think about actually removing these kinds of biases from language models. And again, there are many different options for doing that. You can do some supervised fine-tuning on a data set that's not biased, or you're trying to correct for these kinds of biases using counterfactual examples. For example, you can try to do unlearning. You can try to use interpretability, for example, interpretable neuron editing, where you identify the neurons that are responsible for, or most responsible for the biases, and then edit them. Or, and this is the simplest possible way, is to do prompting. So, some examples here. You have your usual prompt, whatever is related to your task. Maybe please suggest some place I can go for dinner in Santiago. And then you can say, please ensure your answer is unbiased and does not rely on stereotypes. And just by adding these kinds of requests, the answer will be radically different and will be much less biased. And that's a very interesting finding, and you can apply that for all language models. And so this is surprisingly, the performance is surprisingly good, and sometimes outperforms these other kinds of methods. So we still have a long way to go in terms of understanding how we can actually remove biases from models. Okay. Now something that might be of interest to more of you here, given the posters and so on that I've seen as well, is that an issue that I've pointed out earlier on is that language models don't perform so well on minority languages. And so it's important not just think about languages in terms of, you know, the languages that are spoken, but also in terms of the culture behind the languages, people who speak these languages in different countries. And so there are many people who've now more recently been working on trying to make LLMs more culturally aware, trying to make the outputs more culturally appropriate given what the person requesting the output might be looking for. And so you can see a number of data sets people have worked on, which many of them are still generated by experts and manually generated. Some of them are sourced from the web, and there are some for NLP tasks, for computer vision tasks, and so on. Even within the cultural NLP research area, people have focused on majority languages. So you have English, you can't read this, but you have English on the very left here, and then I think you have, this is closely followed by, I'm just guessing now, I think it's Chinese and Spanish. And then you have lots of minority languages here. So a lot more work is needed for minority cultures too. And also the question is if language is a good proxy of culture or if more should be considered, given that this conference here is a Latin American AI conference. You might disagree with Spain as being considered the main representation for Spanish, right? So people also speak Spanish in other parts of the world. So this should be considered, right? Because every country in which Spanish is spoken has its own culture, and even within the country there are many sub-communities. All right. Then there is also an increasing amount of work on vision language models. So trying to combine language and vision for all kinds of tasks, from image generation to image captioning and so on. And one example that's quite common is CLIP. That was one very prominent vision language model, which did better at kind of aligning text and images so that they can be used for zero-shot prediction. My colleagues at the department, including Desmond Elliott, are also working on combining this research direction of vision language models with that of culture, because well, images are also very culturally sensitive. At the top here, you can see different visual representations of the word, of the concept basketball. Depending on which country in the world you're looking at for a basketball game, the basketball game will look very, very different. And unless the model is somehow taught that there is a difference in terms of the concept across countries, across cultures, it will just not learn that, right? And it's important that all of these different cultures are represented in the training data. Okay, vision language models. It's kind of one of my, so when I play around with language models, this is one of my favorite things to do, to try to get it to generate some images. And this is my favorite recent example. here asked Ali for the ingredients to make a cake and then generate an image of the cake ingredients labeled. And you can see that, well, all of this looks like kind of cake ingredients, so at first glance it looks completely appropriate, but then everything is mislabeled. You have the flour labeled as eggs, and you have the eggs labeled as, one of them is labeled fear, which is quite interesting, and then you have eggs labeled as milk and so on. So I mean, it's really quite wrong. And also when it generally doesn't work very well. Vision language models generally don't do so well at generating text as part of images. So here I asked it to generate a poster advertising the Santiago Carnival, and then I mean the word carnival isn't even spelled correctly, and I said please add some text and make sure you can the text actually shown clearly. None of this is text. I mean, it's just gibberish that looks a bit like text from afar. And this gets even worse when you try to get it to generate text in Chinese or in Korean or so on. Then none of it is somehow actual Chinese or Korean. So yeah, lots of work still to do in this direction. This also brings me to the end of my talk now. Still good? Okay, so Outlook and open topics. So right now we're experiencing a golden era of NLP in the sense that NLP is just can be used by so many more people now, and I think that's a really, really great thing. But it's also a historical turning point, and we've seen other kind of historical turning points in the past. You know, Chomsky grammars, rule-based NLP, statistical NLP, deep learning, and so on. The thing that's very different about this recent era is that NLP is now used by lay people. Also, the resources needed to do NLP development, NLP research have massively increased. Many of the core LLM developments are made by industry and not by academia in terms of actually building LLMs. The speed of research and development has also increased so much because more people are working on LLMs, because people see the benefits of applying LLMs in various settings. But there are also new applications of LLMs, for example, in the humanities, in the social sciences. Even though it seems like many research questions are answered and it seems like many of the traditional tasks are no longer relevant, there are still many research questions that can be asked and studied. And I want to point to some other people in NLP who've voiced the same and probably said it a lot better than me. So there was this keynote by Chris Manning at 2023 who said that NLP is nothing but blue skies. People shouldn't panic. There are many, many things to still be researched. It's not the end of NLP. We're far from done with NLP research. Also, Karen Spark-Jones, that's another famous quote, said, those who have been around for a long time can see old ideas repeating in new guises, but the new costumes are better made of better materials, as well as more becoming. So research is not so much going around in circles as ascending in a spiral. And I think that's also very important to keep in mind. And even though I've not been in the field for that long, I can also see it by observing trends in the field. All right, so many different possibilities for future NLP research, including the things that I've mentioned during the talk. There are still factuality issues. Prompt instability more broadly is a massive issue. Better evaluation of language models is needed. More work on interpretability, more work on bias and fairness evaluation, on cross-cultural aspects, on multimodality and vision language models. Also something that I haven't mentioned but that is very important is on carbon footprint development. We need smaller models. We need models that can run on mobile phones. We need models that can actually be used in smaller companies and in academic labs, not just these bigger models, because they use way too much energy. So that's another very important area. And many different applications still possible, and also different directions for interdisciplinary research. And if you don't believe me, then also have a look at these papers. So other people have tried to say the same thing and also listed some potential research questions. And you can see from some of the titles how panicked some people were. So choose your weapon, survival strategies for depressed AI academics. Has it all been solved? Open NLP questions not solved by large language models, and so on. So have a look at these papers as well, if you're looking for some inspiration. Okay, so this brings me to the end of my talk. I'd like to say thank you. Could I quickly put the slides back on for a second? Just 1 second. Okay, it's not coming up, but I want to say also thank you to my research group, without whom I wouldn't be, without whom I wouldn't be standing here today. They're all doing excellent research. And if you're looking for some PhD interns, for in industry labs, they're all looking. And also have a look at our recent publications. And I don't know if you have any questions, any time for questions.
Yes, we do have some time for questions. First, thank you very much for a great talk. You didn't disappoint at all.
Okay, that's good.
So, yeah.
Yeah. It's a simple question. When you were showing there the RAG slide, there was something called fusion. What fusion means in that context?
What does fusion mean in the context? Okay, so I can't remember the exact context, but I can tell you what I think it might mean. So you have different kinds of fusion. You can fuse different evidence documents, perhaps. You can fuse different kinds of retrieval strategies. But this was quite a high-level slide trying to summarize different kinds of RAG approaches. So, yeah.
Should I go first? Okay. Thank you for your talk. You just talked about, mentioned that the speed of research has increased a lot in the past years. So I wanted to ask you your own opinion about how that idea relates with the decision of whether to publish in journals or conferences. So what do you think about that? Because I think that in AI in general, we have like a sort of flag planting or sort of that race where we want to publish as quick as possible, and journals do not follow that logic. Or maybe I think that. So what do you think about it? Thank you.
Yes, good question. So I still occasionally publish in journals, but then I go for open access journals that have a faster turnaround. For example, there's the TACO journal and Computational Linguistics journal. And there you can also put the paper on archive while it's still under review. So then you don't really lose out on the flag planting opportunity if that's what you want to go for. But journals have the advantage that you can study a research question in more depth. And to the reader, they're usually more interesting than conference papers, because then there's less space for error analysis and so on, additional ablations and such. So I really value journal papers, I would say.
Hi. Yeah. So you mentioned prompting a model can help with biasing. I wonder if that could be like a fake correction, in the sense that maybe you correct that particular bias that you prompt towards to, but there are other biases that you didn't think about it, that maybe the other techniques may solve easily, or if you have seen that prompting for a particular bias help in other categories.
Yes, very good question. So the thing with language models is they've seen so much different text that one can say that they're biased, but also it really depends on what kind of regions of the parametric knowledge are activated, and they're activated by different kinds of prompts. So if you phrase your prompt in a way that says, please don't output something biased, they might not. They might somehow draw on the knowledge from less biased documents or such. But the bias is still there, and you're completely right. And that's why there are methods to try to address that more systemically by looking for biased neurons and neuron circuits and then removing these biased neurons. But this also has some ripple effects. So because individual neurons aren't just responsible for one thing, they're responsible for multiple different things. So you can't just somehow sever the connections and expect everything else to still work in exactly the same way. So it's quite complicated. And then of course there is unlearning, and that can also be used, but then you need to have a data set that's annotated for it, and you need to think about what is bias and so on. So there is no great answer to this. There are just multiple options depending on also what kind of access you have to the language model. Yeah.
First, thanks for such a great talk. You showed a lot of the problems that today we have with the LLMs, and you also showed some techniques that we can use to handle them, right? And some of them implies using more LLMs, right? So we are not having just a model, but a system where we use more LLMs to solve these issues. And I want to ask about your point of view on how this will impact the interpretability of those systems and not now like just a model, either in a positive or a negative way.
So I think I mentioned earlier there's, in terms of evaluation of language models, a very common approach is LLMs as a judge. So then the idea is you have one LLM that you're testing and you have some other LLMs that you're using to judge the outputs of the first LLM. And of course this can be done, but then, and in practice it performs decently well, but the more principled way is still to do a manual evaluation. But it's just really difficult to do it when, and very costly to do. And that's why people use LLM as a judge also, because it can then be done during training and thereby improving the language models as they're trained. So yes, and of course this might reinforce some biases. So if you use an LLM that's biased, and I mean, then of course this will reinforce the biases that already exist. So it's important to always do human evaluation as well, at least at the very end of when you've developed all the models, you compare maybe the main ones and evaluate them directly using human annotations.
Thank you.
Hello. Oh, sorry. Well, thanks for your talk. I want to know those things that you shared, that the model's performance changes depending on how the model is prompted, like the style of the prompt for each model. Does it make sense to kind of learn how to prompt each model as if it were a kind of language in the middle term, or it's more we will expect that in the future they will tend to use like a common language?
Yes, so there's been a lot of work on prompt engineering, which was exactly about that. What kinds of prompts to use for individual models to get the best possible output. I don't work at one of these major companies designing language models, so I can't tell you what exactly they're doing, but what I'm hoping they're doing is to look into prompt stability and try to address the underlying cause as well. And this research that I've shared with you on automatic prompt tuning is one way of going, where you use multiple language models, you look at stability and you try to improve it automatically using some reinforcement learning based approach. So I mean, this thing of trying to work out which prompt works with which model might be something you want to do in the interim, but in the longer term I really hope that it will be improved by those working on designing the large language models.
So thank you everyone. we run out of time for questions, but we have the coffee break now, so questions can continue there. And I have just a couple of announcements before you move there. Thank you. So as I said, now we have the coffee break, and then we have the practicals. Remember to start going to the practicals 15 minutes before, because 2 of the practicals are going to be in this building, that is economy. These are for the people that want to go to the practicals in room PC2 and room PC1. This is in this building. You have to go up 2 floors and go to the computer rooms 1 and 2. For those that want to join the introduction to transformers with Jax, you have to move to another building that is an engineering building for the room K203. This information is now in the web page also. And also here you have a little map that shows that you have to walk for 5 minutes to get to the engineering building. Okay, there will be volunteers and people going there. Yeah. So, and then make sure to come back here, because we will have the Make Your Own KHIPU and Welcome event here in the auditorium. So now you can go to the coffee break.
2. Prueba de audio.
Hello. Sí. Mm. Pero no sé en cuál más ponerlo que en Hello. My name is Jocelyn Dunstan. I'm a professor at the... Se cae.
Era lo que estaba pasando en el computador de nosotros. ¿Te fijas? Nosotros lo que hicimos, pusimos otro computador que tiene entrada de red directa para que funcionara más rápido en internet. Entonces, yo creo que si le pone un adaptador debería funcionar bien. Pero hay que poner un adaptador por la parte. O uno con USB normal también. O para USB normal, pero que tenga un puerto electrónico de red. Porque el Wi-Fi es necesario para funcionar.
Hello. My name is Jocelyn Dunstan, and I am a full professor. Sí. Pero había que traducir. Eso se pone lo que... ¿eh? Hello. Oh, oh. ¿Sigue diciendo lo de Internet Connection? ¿Estará conectándose?
Es que lo que pasa es que le pusiste la Mac.
No.
Tienes que eliminar el si no te toma, después tienes computador, tienes que enviar la Mac al informático acá de la universidad para que te lo habilite.
1, 2, 3.
Pero la ha pasado otra vez, así que no tema de un tema eléctrico del lugar. Interferencia. Sí. ¿Y el pollo? Ah, el pollo está apagado. Ojo que si todo lo que estamos hablando se está haciendo con... E2.
Please take your seats. We are about to start. We're already 15 minutes. That's Latin America. Hi everyone. So it's a great pleasure because today we are building our own KHIPU, and it's going to be Patricia Romero from Museo de Arte Precolombino that is going to teach us. So today is about her. Just a little thing, you have little tables so you can pull them up because it's going to be easier to build your KHIPUs. And Patricia is going to make an introduction, but as the live translation is working more or less, I'm going to just translate at the beginning. And then while she makes the KHIPU, she's going to speak really slowly and you're going to see exactly what she's doing. So if you have like any question or something, you just raise your hand, but I'm not going to translate like everything, otherwise it's going to be like really, really slow. So Patricia, please. No. Ahora, creo que no. Ahora. No, para que no ahí vienen. ¿No se escucha? Sí. Pero están viniendo corriendo para ayudarte. Porque no está prendido, creo. ¿Puede ser? ¿Está apagado? ¿No? ¿Ahí? ¿Sí? ¿Se escucha? No. Está como apagado, si no. Pero ahí anduvo. Ah, ahí estaba el on-off, con razón. Ahora.
¿Ya? ¿Aló? Sí. ¿Sí? ¿Ahí sí? Ay, muchas gracias, estoy muy emocionada. Primero a la organización, gracias por haberme invitado, al Museo Chileno de Arte Precolombino también. Este curso yo siempre lo hago en chiquitito, así que esto para mí es muy nuevo, que sean tantos participantes, y estoy feliz de que tanta gente esté interesada en aprender esto. Yo me llamo María Patricia Romero, pero nadie me dice así, me dicen Icha, así cualquier cosa, Icha. Yo soy investigadora textil y también hago clases. Pero también yo de profesión le estaba contando que soy bioquímica. Entonces, inicialmente yo pensaba que no tenían ninguna conexión, pero después uno se va dando cuenta que algo tienen en común, las estructuras, las lógicas de cómo se van armando todos estos textiles, tiene harto que ver.
So,
perdón.
Of course, I'm not going to say everything that she said, but she's really excited to be here. In general, these workshops is just for small people, so it's her first time. So be nice with her, please. And in fact, she's also a researcher, but she learned biochemistry, and we were talking about that. At the beginning, she thought that it had like nothing to do like doing these workshops, but she does research in textile. So it has a lot in common, science and knowing what happened there.
Sí. Bueno, les voy a dar un poco de contexto de los KHIPUs. En general la gente como que ha escuchado sobre los KHIPUs, como muy en general. Yo les voy a contar un poquito de qué se trata. Este es un sistema de comunicación andino que se trata sobre cuerdas y nudos, ¿ya? De comunicación, de registro a través de este sistema tridimensional. ¿Te doy?
So, as you're in KHIPU, maybe you already heard about KHIPU, so she's going to tell you about this. So it's language. So it's a way of communicating things, and it's about numbers. Y también letras.
Sí, también narrativo. Es numérico y narrativo.
Okay, so it tells stories also, not just only numbers.
Claro. Los KHIPUs que se han encontrado cumplen, como que los podemos agrupar en dos grandes como conjuntos. Uno que son los KHIPUs numéricos, que son los que vamos a trabajar ahora, que son los que están más descifrados, que cumple ciertas reglas y se ha podido leer y es lo que yo les voy a enseñar. Y están los KHIPUs narrativos que no cumplen ninguna de estas reglas que les voy a explicar.
So there are two big clusters, the ones that we are going to learn about, that are the numeric and are the ones that have been decodified in fact, so that are the more understood. And then there are the other ones that tell stories, but they didn't been codified yet, so we are not going to learn anything about them. But we like numbers, so it's okay.
Sí, El contexto igual lo vamos a entender. Se supone que los quipus narrativos contaban las historias de diferentes personajes dentro del imperio, los viajes, las guerras, acuerdos, matrimonios, incluso las reglas que se tenían en el imperio estaban registradas en el quipu. El quipu quedaba registrado en la información y viajaba a través de todos estos caminos de los incas para ser comunicado a otros lugares.
Long story short, it's like a newspaper that went from one village to the other ones, like telling the whole story. So this, not the number quipus, the other ones, that tell about everything that happened in the empire in one part of the empire, and then would travel like for the Inca, for all the Inca ways.
Y hay diferentes teorías de cómo funcionan estos quipus narrativos. Yo se lo voy a dejar así porque como ustedes, de más que en diferentes cabezas, nacen diferentes teorías, también para que lo piensen en sus casas. Hay teorías que dicen que son tridimensionales, que los nudos podrían ser sílabas, por ejemplo, y al combinar estos nudos podrían formar palabras, pero yo soy más de la idea de que quizás los nudos son ideas. Entonces, un nudo, por ejemplo, puede significar el nacimiento, otro puede significar viajes. Entonces, al final, la combinación de estas ideas hacen una historia.
So there are different theories about how they worked. Some people think that there were like three-dimensional quipus that had like some words, and there were like words codified in them. But Icha believes that it's more like ideas, like born, like more concepts that were put together.
Claro, tiene que ver con la forma de cómo expresarse. Cuando uno piensa en sílabas, como que uno está pensando en cómo lee uno ahora, y no creo que tenga que ver con esa lógica. Ya, pero nos vamos a enfocar más en los numéricos, que es lo que les puedo enseñar más a fondo. Los quipus numéricos tienen algo súper especial, que tiene zonas súper conservadas. Si se fijan en el primer quipu, bueno, y en el de abajo también, se notan zonas. ¿Lo ven? Zonas de nudos.
So no, so the quipus have like different zones that are codified in there.
Claro, entonces se nota inmediatamente que este es un quipu numérico, ¿ya?
So that's the way that you can see that's a numerical quipu and not a storytelling quipu.
Claro, entonces así pueden diferenciar uno de otro. Y como datos curiosos, por ejemplo, se registran más de 800 ejemplares que están en el mundo conservados, pero como hablábamos antes, es súper relativo. Hay colecciones privadas también donde no se tiene ingresado la existencia de esos quipus.
So there are more or less 800 quipus that are registered, that exist were found and conservated, but probably there are in some private collection that are not registered yet.
Y también es importante saber eso porque eso es un problema dentro del estudio porque están muchos descontextualizados. O sea, se encuentran en tumbas, las saquean y se los llevan a otros lugares y luego se encuentran esos quipus y no se sabe con qué, por ejemplo, cuerpo está asociado, con qué otros objetos, dónde se encontró. Entonces, después hacer el match de qué es lo que significa ese quipu es súper difícil.
So this is a problem because some of the quipus were just taken from one place and taken from the other, and they weren't registered where did they come from, to which culture or body were associated. So it's really difficult to decodify what they meant because they don't know the other information that was associated with them.
Claro. Y uno de los más extensos tiene más de 1500 cuerdas. Para este curso yo hice sus materiales, todas esas cuerditas que ustedes tienen en sus manos las hice a mano y son 1200 cuerdas, así que casi, casi soy yo. Si las pusiera en una sola cuerda sería más o menos eso.
So if we join all the strains that you have in your hands that were built by Patricia, so she did that by hand, from the fleece to what you have already there, it would also be like the longest quipu that is registered yet.
Sí. Bueno, y voy a mostrarle un poquito sobre la organización, porque se dice que los más grandes tienen 13 niveles de organización. Para que entiendan eso, les voy a mostrar una maqueta que hice del quipu.
So the biggest ones have 13 levels of organization, so she built an artificial quipu just to be able to explain that.
¿Se ve, cierto? ¿Sí? Ya, los quipus se componen de una cuerda principal, que es la cuerda madre, que es la que estoy sosteniendo acá, que generalmente es de mayor calibre, más gruesa. Y de esa cuerda, de la cuerda madre, cuelgan otras cuerdas, que son estas cuerdas como primarias o cuerdas colgantes, ¿ya? Estas de acá. De estas cuerdas primarias o colgantes pueden colgar cuerdas secundarias, que son estas, y de la secundaria podría colgar una terciaria, una cuaternaria, y así poner 13 niveles diferentes de organización. Y estaba hablando con los chicos, con los voluntarios, claro, uno empieza a pensar cómo organizaría la información. Entonces, jugando con estos niveles y a ir anclando unas de otras, puede organizar esta información como a uno le parezca mejor. Se la hice difícil.
And there was no rehearsal, so so the KHIPU is composed about in fact, it's a way of organizing information finally. So it has a mainstream, and then there are other strains that are going to be entered, but these strains can have like another level, and then another level, and then another level, till going till 13.
Claro. Entonces, además se encuentra a veces una cuerda que es superior, que está acá. Esta cuerda superior, espérame, acá está. Esta que va hacia arriba, o sea, si uno lo toma así, todas van hacia abajo, pero se nota por cómo está estructurada que va hacia arriba. Y esta muchas veces resume la información de abajo. Es como para comprobar que la información de abajo está bien. Muy complejo. Sí, excelente.
So sometimes there is just a main strain that you can recognize it because the knot is not like built till the bottom, but it's built to the up. So you could like confuse it and say that everybody is going down, but as you see how the knot is built, then you can infer that this one is going up. And sometimes it like has all the information that is in the bottom part. So it's like so it's not a codification, but it's a verification digit that verifies that the all information going bottom is resumed upwards.
Excelente. Bueno. Y sobre esa estructura de cuerdas van los nudos. De hecho, KHIPU significa nudo. Y KHIPU con la Q significa, bueno, es lo mismo KHIPU con K y con H, eso está en la lengua quechua, y KHIPU con la Q y la U está en español, ¿ya? Así que lo pueden encontrar indistintamente de una u otra forma, ¿ya? Así que para que no haya esa confusión. Bueno, esa es la estructura.
So the KHIPU with K and H, it's in the Quechua language, and then you can like write it in Spanish with like the Spanish alphabet. So, but they are both the same.
Ya, súper. Entonces, vamos a ver un poquito más. Las cuerdas. Lo primero que hay que hacer es construir las cuerdas. ¿Podemos pasar a la cámara? Ya, vamos a empezar de lo súper básico. Esquilas, por ejemplo, un animalito. O recolectas los copos de algodón. ¿Sí?
So there's a sheep and you take some fleece. Or just you go from the field and there's cotton that you found and it's like...
En este caso, esta es lana merino, ¿ya? Y les voy a mostrar cómo se hacen los primeros hilos. La lana se estira y se tuerce. Al momento de torcerla, tú tienes un hilo, ¿ya? Entonces, dependiendo de qué tanto lo estiro, es qué tan fino va quedando. Nosotros actualmente empezamos de una lana lista, que es como la lana que tienen ustedes ya en sus manos, ¿ya? Entonces nos saltamos esta parte.
We understood that. No, it's like
¿Se entendió?
The way from how you go from the fleece to having like the strains that you have, you are not going to do like the fleece part because it's like, well, nowadays it's doing industrial way, but before it was done by hand.
Pero es importante que entiendan esta parte porque los quipus y bueno, y todos los textiles precolombinos parten desde acá. O sea, ellos no tenían ni una opción de tener el material listo. De hecho, era planificado de mucho antes. Se cultivaba o se tenían animales pensando en el textil que se iba a tejer. ¿Sí?
So when the people, natives were in Latin America, there was of course no industrial ways. So if you were going to do a KHIPU, like you have to plan like really before because you have like to grow the animals, grow the wool, then take the wool from the animals, then have the fleece, wash the fleece and everything, and then so it was like really artisanal and it took like long time.
Y algo muy bonito es que acá en la zona andina existía algodón de colores. Existía algodón rosado, morado, verde, café, amarillo. Algodón, algodón, algodón. Sí, algodón. Existía algodón de colores y se dejó de cultivar porque era más fácil tener el blanco y teñirlo. Entonces, cuando llegó toda la invasión española, se dejó de cultivar y se potenció mucho más el algodón blanco y ahí se perdieron. Ahora hay proyectos que están recuperando esas variedades, pero claro, está difícil.
So there existed cotton that was already colored from the plants, but then when the Spanish came and they knew how to come from the white to the colors that they wanted, then they stopped like cultivating the other colors. With the wool is something the same, about the same, like people like put like the sheep, like the brown sheep away, but now they are like
bueno, las ovejas llegaron con los españoles, yeah. O sea, acá existían alpacas, guanacos y algodón, y después ya con la llegada de los españoles se incluyó la oveja.
Okay, before, so the sheep came with the Spanish people, with the colonizations, but then there was llama and alpaca and so on, so they had the wool from those animals.
Super. Entonces, ya teniendo los hilos, ustedes van a empezar a trabajar y a mover las manitos. Ustedes tienen dentro de sus materiales esto, ¿cierto? Van a soltarlo y liberar todos los hilos, ¿ya?
So now I'm going to stop translating because you are going to see anything that the teacher is doing. It's the funny part, I know, yeah, but that's not meant to be like that. Yeah. So, but if you have like any doubt that there's something that you didn't understand, please raise your hand and then Icha will repeat it or I'm going to translate.
Entonces elijan uno de los colores, cualquiera, ¿ya? Aquí tienen dos opciones, o trabajar solos, si es que son como hábiles para tomar la hebra solos, o pueden pedirle ayuda al compañero para que sostenga uno de los extremos. Entonces van a hacer esto. Fíjense que la hebra tiene una torsión, ya está torcida hacia un lado, ¿cierto? ¿Se ve o no? Ya está, lo voy a mostrar en grande. Por ejemplo, esta ya está torcida hacia acá. Aquí, ahí. Está torcida hacia acá. Entonces, si yo hago aquí, la destuerzo. ¿Ya? Traten de torcer más su hebra. Entonces, miren. Van a torcerlo, van a girarlo. Por eso les digo que si son hábiles, lo pueden hacer. O si no, piden a alguien, al compañero, que le afirme el otro extremo. Tuercen. Van torciendo. Pueden pedirle ayuda al compañero, así aprovechan de conocerlo. Bien torcido. Y cuando está torcido, ahí. ¿Se ve o no? ¿Funciona? No. Tuercen, ¿cierto? Tuercen. Y miren, cuando yo voy torciendo, es magia. Es magia. Toda la energía que voy acumulando hacia un lado, después se suelta hacia el otro. Por eso queda como un cordón. Entonces así se construyen las cuerdas. Mientras más la tuerzo, más apretado queda la torsión. ¿Ya? ¿Sí? ¿Funcionó? Súper. Entonces esa es su primera cuerda. Ahí. Y tienen que hacerle un nudo al extremo. Cuando ya la tengan lista, le hacen un nudo al extremo, para que no se suelte. Ahí. Ahí. ¿Funcionó? ¿Sí? ¿De nuevo? Ya. Toman su hebra y la tuercen. La estoy girando así. Les voy a mostrar con la cuerda más gruesa. Hay que girarla, ¿ya? Hacia el mismo lado que ya está torcida. En este caso yo tendría que torcerla para acá. En su caso tienen que girarla en el sentido horario. Entonces la giran así, tuercen. Juntan los extremos. Juntan los extremos, eso, y ahí debería quedar. Y un nudo, sí. Miren, fíjense que a medida que lo voy torciendo, se va enrollando. ¿Sí? Y un nudo al final. Háganlo con una de las hebras, las otras son para otra cosa. ¿Funciona? ¿Ah? No, lo que dé, el total. Sí. Si lo toman de los extremos, va a dar lo máximo. ¿Funciona? Súper. Igual todas las dudas que tengan después me preguntan, voy a estar afuera. Entonces así, van torciendo y plegando. ¿Ya? ¿Sí? ¿Bien? Súper. Ahí, súper. Y un nudo. Nudo. Sí, que quede firme. Uno trata de hacer el nudo aquí en el extremo, así, en el extremo. Claro, sí, sí, así. Ya. Entonces, lo que tienen ahí es la primera cuerda. Escúchenme un poquito. Silencio. Ya, lo que tienen ahí es su primera cuerda. Es una cuerda sencilla, monocroma, de un solo color. Lo que van a hacer ahora es tomar dos colores juntos y hacer el mismo ejercicio. ¿Ya? Así. ¿Ah? Sí, pueden tomarla, el extremo puede tenerlo la compañera. Sí. Es más fácil si lo toma alguien más, mira, si lo firmas acá, por ejemplo. Yo cuando lo hago en mi casa, afirmo el extremo. Así. Así es mucho más fácil. Entonces, en vez de esta prensa, puede ser su compañero. Y queda así. ¿Se ve? ¿Sí? Y hacen el nudo aquí en el extremo, en las puntitas. Así. Ahí. Queda anudada ahí. ¿Sí? ¿Sí o no? ¿Ya? ¿Va bien? Ahí tienen otro diseño, que es el diseño jaspeado. O sea, tendrían un monocromo, ¿cierto? Acá. Y un diseño de jaspe, de jaspeado. Y hay un... ¡Bien! ¡Súper! Yo cuando le hago esto a los niños, quedan así... ¡ah! Como que es magia. Y vamos a hacer el último diseño de cuerda. Miren. Lo van a hacer así. Van a tomar uno. Atención. Atención. Toman una cuerda, una de los hilitos, y lo dejan así, como un continuo. Y en ese espacio enganchan el otro color. Ahí. Así. Ahí. ¿Se nota? Así. ¿Se ve? Así. Y hacen el mismo ejercicio. La cuerda gruesa, la más gruesecita, es para hacer después los nudos. Sí, esa no la ocupen. Entonces así. Eso. Con la boca, a veces uno puede ocupar los dedos del pie. Uno se la tiene que arreglar. Eso, sí. Y esta última quedó de esta manera, miren. Que es un diseño en espiral. ¿Mm? ¿Esta última? Ya. Deja de desarmarlo. Esta se engancha. Queda enganchadita así. Así. Queda enganchada así. Y tomo los extremos de uno y por el otro lado los extremos de la otra. Entonces les va a quedar la mitad de un color y la mitad del otro. ¿Sí? Y ahí tuercen, eso, y ahí tuercen. En su caso están todo el tiempo girándoselo hacia el mismo lado, ¿cierto? Pero también podrían girarlo hacia el otro. No hay ningún problema. Y queda así. Espiral. ¿Bien? Súper. ¿La última? Ya. La última se enganchan. Deja de desarmar aquí. Se engancha así. Así. Así se engancha. Así. Ahí. ¿Ya? Y lo tuercen. Eso. Ya. ¿Vamos bien? ¿Ya? Ya. ¿Qué pregunta? No escucho nada. Espera. Silencio un poquito. En el extremo donde están las colitas. Se llama nudo paralelo, mira, te muestro. A ver, deja mostrarte un extremo. Si estos fuesen mis extremos, se toman así. Y se anuda. Así. Todas en la puntita. Es importante, miren. Miren, pongan atención. Es importante que en un extremo va a quedar ese nudo que le acabo de mencionar y en el otro extremo queda continuo. Yo puedo meter aquí el dedito, miren. Es importante que quede así porque aquí es donde se engancha el KHIPU. ¿Ya? Si yo esta cuerda la quisiera enganchar en mi cuerda madre, se hace así, de esta manera. Ahí. Y se pasa la colita por dentro. Ah, así. El último queda más anchito, sí. Sí. Lo repito. ¿Qué repito? ¿Esto? Este se engancha, así. ¿Cómo se engancha? Ya. Se engancha así. Les decía que a un extremo es importante que esté el nudo. Si ustedes no anudan, se va a desarmar. Y en el otro extremo queda un continuo, queda un loop. Así. Queda el loop. Y aquí, dentro del loop, pasa la cola. Y es así como están enganchadas las cuerdas en su llavero. Así. ¿Van bien? No se demoren tanto en esto que nos faltan los nudos. Así que apuren. ¿Sí? Pueden engancharlo ya si quieren, pero vamos a ocupar la cuerda gruesa para los nudos, así que no lo ocupen. Pueden engancharlo entre sí, por ejemplo, para que no se les pierdan las cuerdas. Pueden tomar una como cuerda madre y enganchan la otra. Dejan enganchadas entre sí las cuerditas. Así, miren. Yo enganché una de mis cuerdas a la otra. Entonces, en este caso, atención, en este caso esta sería mi cuerda madre, muy chiquitita, muy resumen, y esta es una de las cuerdas primarias o colgantes. ¿Ya? Entonces, déjenlas enganchaditas entre sí para que no se les pierdan. ¿Ya? Y para que entiendan cómo se enganchan. Sí, se abre, es como un loop. El loop. La que quieres enganchar, la que se va a enganchar a la madre es la que se abre. ¿Sí? Entonces, ahora quiero que pongan atención en las cuerdas que hicieron. ¿Ya? Tienen una torsión. ¿Se fijan que se ve como una diagonal? En las cuerdas que ustedes hicieron, se ve o así, dependiendo cómo hayan torcido. Las cuerdas tienen como una nominación según la torsión. Por ejemplo, esta torsión es en Z. Se le dice Z porque forma una Z. Si yo dibujo una Z por aquí, el palito de la Z coincide. ¿Se nota, no? El palito de la Z coincide con esta diagonal. Si está torcida hacia el otro lado, se le dice torsión S. ¿Ya? Y no es que yo pueda llegar y tomar esto y dar la vuelta. Pues sigue siendo Z. Porque uno intuitivamente hace esto, como que la va a cambiar. No, no funciona así. Tendría que estar torcida hacia el otro lado. Así. ¿Sí? ¿Se entiende?
So the names of the ways of twisting that chord is that, as Icha showed, if they show like a Z pattern, did you saw that part of the Z pattern that Icha showed? Mostrarla
Sí. ¿Se puede ir al compu?
Okay.
Ahí se nota. Entonces, vamos a intentar aquí dibujar. Por ejemplo, aquí se llama Z porque uno hace una Z así. ¿Se ve o no que la diagonal coincide? Y en cambio en la S coincide como la parte larga de la letra, coincide con eso, miren. Esa parte de ahí coincide. Y esa parte de ahí coincide. ¿Sí? Es importante porque eso también nos da información de la cuerda. Por ejemplo, una cuerda, atención, una cuerda, por ejemplo, que está torcida en S, podría yo estar hablando de las mujeres de esta conferencia. Y una cuerda que está torcida en Z, de los hombres, por ejemplo.
So the way of for this twist could have some information. For example, S could be the females of this conference, and Z could be like the males of this conference. So it's the way of as they codify.
Claro, nos da información, porque al final cada cuerda tiene una identidad. Por ejemplo, esta cuerda me habla sobre mujeres, o quizás me habla sobre mujeres y esta me habla sobre niñas. Y esto van siendo como subcategorías y me va dando información de la cuerda. ¿Se entiende, no?
So the way as the chords are attached and twisted gives us information. For example, one chord could be the females, but then other chords attached to this one could be like the girls or
Claro. Entonces, todas las componentes de una cuerda me va a ir dando información. El color de la cuerda, el material de la cuerda, hacia dónde está torcida o incluso cómo está anclada. Para anclar, es lo que le mostré antes, se ancla de esa manera, se abre ese loop y se engancha. Y se puede enganchar hacia un lado o hacia el otro. Uno se llama recto y otro se llama verso. Y eso también me da información.
So this is one example as how they are anchored. The way as you anchor also gives information. So one type of anchoring is called recto and the other type of anchoring is...
Claro, esos sí son intercambiables. O sea, si yo hago esto, cambia de recto a verso. Pero entre ellas son distintas.
Okay, so like if you take the KHIPU on the other side, then recto anchor could transform it in the verso anchor, but if you see like all the knots together, then the information, if they are from in one side or the other side, gives information.
Súper. Ya, y ahora vamos a los nudos. Ya sus cuerdas están preciosas, ¿cierto? Ya les funcionó. Ahora vamos a los nudos, que es una parte muy importante. Para eso tienen la cuerda que es un poco más gruesa, la blanca, ¿ya? Ahí vamos a practicar los nudos, ¿sí? Entonces, los primeros que vamos a hacer son los nudos simples, que está ahí. El nudo simple se lo voy a hacer con una cuerda más gruesa para que lo puedan ver, ¿ya? El nudo simple es el típico nudo... cámara. Por favor. Ya, lo voy a hacer con esta cuerda para que se note más. El nudo simple es el típico nudo que uno hace. Nada más. Y ese nudo, ya, ahora se los puedo complicar más. Ese nudo se puede hacer también en S o en Z. Se puede hacer hacia un lado o hacia el otro. Depende para dónde empiezas. Ahí.
So the way that you build the note, it also could be in Z or East, depending on which one of the chords you put like in the upwards.
Y esto se ve aquí. Si se fijan por adelante se ve así el nudo, pero por atrás tiene como una diagonal. Entonces aquí uno dibuja la letra y esta sería S. ¿Se ve? Lo voy a hacer hacia el otro lado para que se note la diferencia. Miren la diagonal, ahora está en Z. Entonces uno lo hace como sin pensarlo siempre, pero uno está anudándolo hacia un lado o hacia el otro. Y eso también nos puede dar información. En general, las cuerdas está toda la cuerda anudada hacia un lado. O sea, o toda la cuerda está anudada en Z o toda la cuerda está anudada en S.
So in general, the pattern of the knotting, it's always the same. Either it is all S or all Cs in the same chord.
Y eso también nos da información. O sea, ya tenemos material, color, tenemos el enganche, si está en recto o en verso. Y tenemos esto, hacia dónde está anudado. Entonces tenemos muchas categorías que nos pueden dar información de la cuerda.
So we have several types of information, the material of the core, the way of the knots are done, the anchors also, so it's like adding and adding more information.
Así, así. Nudo simple, ese es muy fácil. Sí, para practicar. Tienen que ir armando y desarmando, ¿ya? Entonces el nudo simple es muy sencillo. Y cuando uno ocupa este nudo, es en las partes de arriba. ¿Podemos volver a la presentación? Ya. Los nudos simples se ocupan acá. Las cuerdas de los quipus numéricos están separadas en zonas, ¿se acuerdan que yo les dije? Entonces, las diferentes zonas representan como las partes del número. Por ejemplo, aquí hay 3 zonas. 1, 2, 3. Aquí arriba van a estar las centenas, aquí las decenas y aquí las unidades.
So this is the way of the numerical quipus are built, and she already told us about the zones. So in this example, then the first part would be the hundreds, then the other part would be the tens, and then the other part would be the units. So you see in the general quipu how these zones are defined.
Por ejemplo, en ese de allá tenemos más zonas, tenemos 5 zonas, ¿ya? Entonces uno como a simple vista puede distinguir las zonas. Entonces los nudos simples van a ir aquí en centenas y en decenas. En verdad todo de aquí para arriba, menos en unidades.
Okay, so the simple knots are going to be in the hundreds and in the tens, but not in the units.
Entonces, si yo quiero decir 100, voy a tener un nudo simple, que es el que acabamos de hacer, en esta zona de acá. Si quiero decir 200, voy a tener 2 nudos juntitos, unos con otros, así, en esa zona.
So the number of knots tells the number of hundreds. For example, if it's just 100, then it's going to be just 1 knot, but then if it's 200, then there are going to be 2 knots that are going to be close between them.
Claro, hasta 9. Y a veces están tan juntos los nudos que parece un solo nudo. De hecho, si ustedes se fijan después en el quipu que está colgado afuera, van a ver que esos nudos como largos son varios nudos juntos.
So if the knots are like really, really tight, when you see them, you feel like they are like just 1 knot, but in fact they are simple knots that are really tight together. You can observe that in the quipu that Icha generously did also for us.
Entonces tienen que
Tomorrow we are going to reveal what's in that quipu.
Es un misterio, ahí les voy a decir, les voy a dar la tarea. Entonces tienen que intentar dejarlos bien juntos. Eso a veces es un poco difícil, que queden pegaditos unos con otros. ¿Ya? Ese es fácil, ¿cierto? ¿Sí? ¿Fácil? ¿No? ¿Ah? No, no arriba, al lado, pegaditos unos con otros. ¿Puedo ir a la cámara? Así, pegadito uno con otro. Mira, uno, otro, otro. No, no arriba, que no quede así como montado. Mira, que no quede así. Eso está mal. Entonces, por ejemplo, estos 3 nudos pegaditos unos con otros, podría ser 30, si es que está en la zona como de más abajo, podría ser 300, 3000, 30.000, dependiendo de en qué zona de la cuerda está, ¿ya? Entonces hay que ver el contexto, no es que este nudo por sí solo me dice qué es, ¿ya? Tengo que ver el contexto. ¿Fácil hasta ahí? ¿Qué cosa? No, solo que la practiquen en la cuerda blanca, en la que es más gruesa. Esa se las dejé para que practicaran los nudos. Sí, la cuerda blanca se la dejé para practicar los nudos porque es un poco más gruesa. Ah, ya, sí, esa es una súper buena pregunta. ¿Puedo ir a la presentación otra vez? Perdón por tanto. Ya, si yo quisiera decir 0, por ejemplo, si quisiera decir 101, acá no tendría que haber nada. Está libre ese espacio. Por eso es súper importante que se marquen claramente los espacios. Si está medio difuso, no se va a saber cuándo no hay un nudo. ¿Ya? Tiene que estar muy claro. ¿Ya? Entonces ustedes van a ser muy ordenados para escribir.
So the zones are really important in how you build this because, for example, 0 is represented by nothing. So there's not going to be a knot in the place of the hundreds, for example, or in the tens here. If you want to say like 101, then you wouldn't put a knot in the tens zone. So you have like to be really careful for building this because the zones have to be like really understandable from.
Super. ¿Alguna otra pregunta? Sí, dale. Generalmente no hay una cuerda sola. Hay muchas cuerdas y en el conjunto uno entiende cuántas zonas son. Sí. Igual también hay ahora les voy a explicar, hay un nudo especial que es el nudo largo, que son de las unidades. Entonces también te da el cierre. Tú sabes que ahí termina el número. ¿Ya?
So there's always to be context to understand which number. It's like you're not going to find one knot alone and then there's no other information. But there's one that is the one that's closing, that's the units, and it's going to be a large knot.
Claro. Es súper importante el contexto porque uno no podría saber cuántas zonas hay. Sí. ¿Ah? Oh, no escucho nada. Allá. No, solamente la cuerda blanca, la que es un poco más gruesa, se las dejé para que ustedes practicaran los nudos. Lo que van a escribir es en el llavero. Sí, es solo para que practiquen, armen cosas, desarmen. Su trabajo final es el llavero.
So, this one, the biggest one, is because it's easy to knot and unknot. So,
claro.
So it's just for practicing.
Sí,
so this is not going to be
así.
like the mother core, don't worry about that. We are going to build the KHIPU in the keychain. So
Claro.
the keychain that you had in your little pocket that we gave you at the beginning, it's going to be your mother core. ¿No?
¿Alguna otra pregunta? Allá. Sí. ¿Allá? Espérame, no escucho. Ese sí.
So this is going to be, if you don't find the keychain, don't worry. Then you're going to attach your keychain to this one. Not keychain, the keychain. Your keychain is not. But this is going to be the principal, the mother core. So don't worry.
Ella tiene una pregunta. Si hay una técnica para que el nudo quede ¿qué? Ah, para que quede en el lugar donde uno quiere que quede. Ah, es como uno lo empieza. Si uno lo empieza siempre hacia la derecha, siempre te va a quedar hacia un lado, por ejemplo. Si el movimiento inicial es siempre con la cuerda por encima, hacia la derecha, siempre te va a quedar en una dirección. Si siempre empiezas con la cuerda hacia la izquierda, te va a quedar siempre en la otra dirección. Depende del movimiento inicial. ¿Puedo ir a la cámara?
Translation.
Miren.
So,
acá está la cuerda.
on.
Si ustedes empiezan así el movimiento y después pasan por abajo, les va a quedar en Z. Si empiezan hacia el otro lado del movimiento con esta cuerda por encima y hacia la izquierda, les va a quedar en S. Entonces, ¿toda la cuerda debería estar anudada en S o toda la cuerda anudada en Z? En este caso no me voy a preocupar tanto, pero ustedes tienen que saber que existen esas dos formas de anudar que también nos pueden dar más información.
So in general, the way that you start the knot is if it's going to be Z or S. The important thing is that you keep the same pattern. So it doesn't matter if you just build Z or S nodes. The thing is that you keep the same pattern, but nobody's going to judge you if you do like the knot on the other side. So don't worry, it's not
Sí,
that big.
es un taller básico, así que tranqui. Es su primer taller. ¿Ah?
You choose the one.
Sí, pueden elegir. Ya. Entonces, ahora vamos a ir a los nudos más difíciles. Esos eran los fáciles. Entonces, puedo... Ah, no, está bien con mis manos. Ahora vamos a ir al nudo largo. Los nudos largos van en las partes de las unidades. ¿Se acuerdan que yo les dije que de las decenas hacia arriba había nudos simples y pegaditos unos con otros? En el último, en la unidad abajo, van a ir estos nudos largos. Y son así. Vamos a empezar desde el 2, después voy a ir al 1. Ya.
So now it's really important because Icha already explained that from the tens to the hundreds and so on, the amount, the units are like counted in knots that are independent but tied together. For the units, that's so to know which is with the end is, then you're going to build large knots. So so she's going to start with number 2.
Sí.
So pay attention.
Luego el 1 porque es un poco más difícil. Entonces, vamos a empezar con...
It's more difficult than the 2, so we are beginning by the 2.
Empezamos con el mismo movimiento inicial, o sea, la cuerda pasa por encima, ¿ya? Y vamos a pasar como si fuera un nudo simple, así, pero vuelves a dar otra vuelta dentro. 2 vueltas. Y ahí queda un número 2. 1, 2. ¿Sí? Lo voy a repetir. Lo voy a repetir. El mismo movimiento inicial, así. Hago como un nudo simple, pero vuelvo a pasar por dentro. Si paso 2 veces por dentro, es un número 2. Ahí. El 3 se imaginarán cómo es. Entonces, el 3, ahí. Empiezo así, igual. 1, 2, 3. Ese es un número 3. Así hasta el 9. Practiquen, yo haría el 2, el 5, el 9. ¿Cómo? No entiendo.
O sea, hacer esto es el nudo simple de 1 al 9.
Es que el nudo simple no se ocupa en las unidades. Se ocupa desde el 2 para arriba y después le voy a mostrar cómo es el 1. Sí. Porque si hago el nudo simple de una sola vuelta, esos solamente se ocupan de las decenas para arriba. Por eso ese no es el 1 de unidad. ¿Ya? Entonces, el 9 se ve más o menos así. Y este es un poco particular porque miren, tiene un cinturón. Y le estaba explicando a los chicos, a los voluntarios, que este tiene un cinturón porque cuando es tan largo el nudo tiende a hacer esto, como a curvarse. Entonces al ponerle el cinturón queda como alineado, queda derechito. ¿Quieren aprender con cinturón? ¿Sí?
So the 9 is...
Ya, pero me lo muestran así, ¿ya?
Ya que explico qué vas a hacer el 9. So the 9 is difficult because it needs a belt, because otherwise it would bend. So she's going to explain how we build a 9. So it should be just a large knot, but you have to add the belt.
Eso. Ya, empieza igual. Ahí. 1, 2, 3, 4. El 5 pasa por fuera. 5, 6, 7, 8 y 9. Y hay un truco para estos nudos que son largos. Siempre hay que tirarlo como hacia abajo, miren. Así. Para que quede ordenadito. Como que uno los desliza hacia abajo. Y ahí está con cinturón. El 5 envuelve. No pasas como por dentro, sino que alrededor. Es el más difícil, yo creo. No es necesario que siempre el 9 sea así. Yo he visto sin cinturón y no hay problema. ¿Ah? Solo para el 9 porque es muy largo. Miren, si tratan de dar 9 vueltas van a ver como que se va a curvar y se ve como una bola. Sí. Como que se ve como una bola si no tiene cinturón. Pero se puede. ¿Cómo van? Voy a repetirlo. Voy a hacer el 3. Ahí. El movimiento inicial, ¿cierto? Ahí. Ahí. 1, 2, 3. Y les decía que lo más fácil en estos nudos es deslizarlo hacia abajo, así. Hay que tirarlos hacia abajo, así. Ahí. Ahí. Para que quede ordenadito. Igual los primeros quedan desordenados. Así. Y se cuenta acá. Y es muy importante esto porque es un sistema que es multisensorial. O sea, es un instrumento que se ve, o sea, ustedes ven aquí, ¿cierto? Ven la división de las cuerdas, ven cuántos niveles hay, Se toca porque, por ejemplo, esto yo lo puedo ver y puedo ver cuántas vueltas tiene, pero cuando uno está hablando de un quipu ya parecido al tamaño de los quipus que se han encontrado, por ejemplo, tú ves ese nudo y no se entiende qué es, ¿cierto? Entonces uno lo toca y al tocarlo se siente cuántas vueltas tiene. De hecho, yo le hago así como en la uña. Entonces, también con el tacto puedo saber qué nudo es, qué material es, hacia dónde está torcido, y además muchas personas dicen que está complementado con un relato. Entonces sería escuchar, ver y tocar. Entonces es un instrumento que es multisensorial. Sí, dale. Te la hice difícil.
So the system, it's not that just to look at it, but you also feel it. So sometimes when the quipus are like really long or have a lot of information, sometimes it's even easier to count it with like uña. Like you use your nail and then it's easier to count how many turns it has to know the unit. And they said that sometimes the quipu came also with a gift, so you can hear it also, so you can see it, feel it, and hear it.
Claro, y la gente que dice que el mundo andino nunca tuvo escritura, no saben nada de lo que están hablando. Como este sistema, que además es tridimensional, es muy complejo. Entonces es muy bueno que ustedes estén aprendiendo.
So people say that the Andean cultures didn't have a way of writing, but people that said that didn't know anything, because now you know that there's lots of information and a way of communicating.
¿Cómo van con los nudos largos? Al principio quedan un poco desordenados, pero uno tiene que aprender a tirarlos así hacia abajo. Y ahí queda ordenado, ¿sí? Veo caras como de bien, caras de aprobación, ya. Entonces, ahí tenemos del 2 hasta el 9, ¿cierto? Y les voy a enseñar cómo es el 1. Atención. Les voy a enseñar cómo es el 1. ¿Tienes pregunta? Sí, ¿podemos repetir el 9 con el cinturón del 5? Ya, acá. Movimiento inicial, ¿cierto? Ahí. Paso por dentro. 1, ¿se alcanza a ver? 2, 3, 4. El 5 pasa por fuera, mira, lo rodea. 6, si me quedo corto. 7, 8 y 9. Pero el 5 es importante que el que pasa por fuera, no pasa por el espacio, sino que pasa alrededor. Entonces como que envuelve. ¿Sí? ¿Se entiende? ¿No? ¿Otra vez? Así. Lo voy a hacer de nuevo. 1, 2, 3, 4. Miren acá, el 5 hace esto, alrededor. Alrededor. 5, 6, 7, 8 y 9. Y ahí queda. ¿Sí? Igual lo pueden practicar después. Piensen que es como que yo le estuviera enseñando como alguien que no sabe escribir, a escribir hoy. Hoy, así de cero.
So don't worry if your notes are not really pretty, because it's like if you were like learning to write. So you're not going to have like the best lettering in the first time, but you're going to have those home and then you're going to be able to practice. So today you're going to practice and tomorrow you're going to
Claro, pueden tener problemas de ortografía y de caligrafía, no hay problema. Sí.
So she's a nice teacher, so don't worry if you don't have like the best.
Eso. Ya, ¿estamos? ¿Ah? ¿Ah? Ajá. ¿Cómo? Ah, claro, que tendría que haber más zonas. Si tienes 4 zonas es que tienes 1000 algo. Si tienes 5 zonas es que tienes 10.000, 20.000, 30.000. Si tienes solo 2 zonas, tienes 10 y algo, 20 y algo, 90 y algo, hasta el 99 máximo. ¿Sí? Ya. Y ahora vamos a hacer el 1. Se ve bonito. Vamos a hacer el 1 de unidad, ¿ya? Que no es igual al nudo simple, acuérdense. ¿Quieres preguntar algo? Ah, ya. Empieza así. Mismo movimiento inicial. Ahí. Pasa por ahí. Por arriba. Por abajo. Haces un 8. ¿Ya? Haces como un 8. Pasa por arriba y por abajo. Y esta colita pasa adentro. Ese es el nudo tipo 8. Lo hago otra vez. Por arriba, ¿cierto? El mismo movimiento inicial. Por abajo, ahí tengo un 8. Y esta cola pasa dentro de acá. Ahí. ¿Ya? ¿Sí? Bacán. Y este también se puede hacer en S o en Z. ¿Bien? Otra vez. Ya. Movimiento inicial. Pasa hacia la derecha y por encima. Después por abajo hacia la izquierda. Ahí. Tengo un 8, ¿cierto? Por arriba y por abajo. Y esta cola pasa por acá. Así. Y tiro. Entonces ese es el 1 de unidad. En la única parte, los KHIPU numéricos, lo van a encontrar abajo, en la última zona. Entonces, por ejemplo, si yo quisiera decir 111, va a haber un nudo arriba, un nudo abajo, nudos simples, 1, 1, y abajo un nudo tipo 8. ¿Se entiende? ¿Sí? Ya, súper. ¿Podemos volver a la presentación? Por favor. Espérame, espera. ¿Ah? Claro, va a estar todo vacío abajo y va a haber un 2 de nudo largo, de 2 vueltas. Si solo 2 de unidad, va a haber un nudo largo con 2 vueltas. Sí.
So let's do a recapitulation. Okay.
¿Ah? ¿Más preguntas?
No.
¿Ah? Ya. Entonces, ahí están. Estas figuras están en un libro, por si quieren, pongan atención. Esto está en PDF, está descargable en el Museo Precolombino. Hay un libro que es de una exposición que hubo el 2003, que es sobre KHIPU. Y está súper bueno, tiene todos estos dibujos.
So you can go to the site of the Museo Precolombino, and there's a PDF with all of the notes, so you can have the book there where you can read. And just to recapitulate, well, because what you...
Sí, dale.
So just to recapitulate, then you have like if you're in the hundreds, in the tens, in the thousands, whatever it is, then you're going to build simple knots that are tied together.
Claro.
Okay,
Acá.
so if it's not units, then you use simple knots. Then for the units, that's where we have either the long knots that we are going to use when we put units from 2 to 9, or if you want to use the 1 for the unit, then we are going to use this special knot that is the 8-like knot.
Excelente. Muy bien. Ya. Entonces, ahora le toca a ustedes. En su llavero tienen 3 cuerdas distintas, ¿ya? A ver qué torsión tiene S o Z.
So which one is the torsion, the twisting of your keychain?
¿Todas
Is
en
an
S?
S or a Z?
Ya. Hay unas en S y otras en Z, ¿cierto? Miren, la alpaca está en Z, la que es negro con mostaza está en S y la otra de nuevo está en Z. Ya aprendieron. Muy bien. Entonces, la idea para este taller es que ustedes escriban su fecha de nacimiento en este llavero. Entonces, todos los llaveros van a ser distintos, ¿ya?
So you're going to use the cord that is in color coffee and beige for the day you were born, then the white that's in black and yellowish color for the month where you were born, and then if you want to, nobody's obliged. You can put the year where you were born or just 1900.
Un enredo así. Misterio. ¿Ah? Nadie sabe. ¿Ah? Ya. Lo primero que deberían pensar es qué distancia tienen que haber entre las zonas. Porque si los dejo muy separados, no me alcanza quizás la cuerda. Yo siempre pienso en el número más grande que podría escribir en un año. Un año de nacimiento de ustedes, 1999. Ese es el que va a tener más nudos. Porque el que nació en el 2000 va a tener 2 y nada más. Bien. Va a salir muy fácil. Nosotras no. Entonces, pienso siempre en el número más grande, 1999, y lo que yo determiné, ¿podemos ir un poquito a la cámara? Es que los nudos, ahí están, miren, ahí está mi primer nudo, ahí, mi segundo, yo escribí aquí 1999. Entonces, entre una y otra tiene que haber como 4 deditos de distancia, pensando en el centro de los nudos. Ahí yo estoy pensando aquí, en el centro de los nudos. Entonces, la distancia entre zona y zona es 4 deditos, ¿ya? Para que lo piensen así.
It's really important to define the zones now. So the way of doing this is like thinking which is the largest number that you could build when you are talking about years. So the largest is 900, 1999. 1999. So, and then there's going to be a distance between the center of each one of the thousands, hundreds, tens, and units. That's more or less a hand. So,
ya. Entonces, por ejemplo, yo nací en el 86. Entonces, en mi caso, tendría que haber aquí un nudo, ¿cierto? Un nudo simple. Aquí 8 nudos juntos, 9 nudos juntos, 1900, ¿cierto? 3, 4, 5, 6,
so this
7,
is the year where
8,
Icha was born.
9, claro, 1900, después tendría que haber 8, 2, 3, 4, 5, 6, 7, 8, y aquí un nudo largo. Para mostrar los nudos largos se pueden hacer así. Entonces ahí sería 1986. ¿Ah? Ah, aquí.
No, es el nudo largo. So she draw. So there is the thousands with just one knot. Then there are the hundreds where she has like 9 knots that are tied together because we are still in the hundreds. Then for the tens, there are little knots that are, so these ones are like not simple knots.
Sí.
And then for indicating that's a long knot, these are these strings that are at the end. So in the 6, you are not using simple knots, you are going to use the large knot where we build one knot that has like multiple loops.
Claro, de aquí hacia arriba son solo nudos simples, unos pegaditos al lado del otro. Y acá son los nudos que tienen varias vueltas. Entonces aquí sería un nudo de 6 vueltas, ¿cierto? Y acá serían 8 nudos simples pegaditos, 9 nudos pegaditos y uno solo. En su caso, que nació en el 2000, 2 nudos arriba y nada más.
So if somebody was born in the 2000,
fácil,
nothing, then they're going to have like 2 knots in the upper part built together, and then it's going to be nothing at the end. But remember that then you're going to build also the month and also the day. So the units are going to be indicated somewhere. So you have to be consistent with the spaces between the hundreds, tens, thousands, and so on.
Yo les recomiendo siempre empezar por el año, porque es la que tiene 4 zonas. Entonces así uno ya determina las zonas para después poder escribir el día y el mes.
So for the people born before 2000, no, and then the other ones also, the year determines the 4 zones, no, and the other ones also. So begin with the year, then you're going to define which the zones are, and then you're going to go to the month, and then you're going to go to the day.
Sí.
There's a question.
No, eso, generalmente los nudos todos en S, o todos en Z, en una cuerda.
So,
sí, en toda la cuerda.
When you start a knot, you put all the knots in the same direction, and the zones are just defined by the distance between the clusters of nodes.
Sí.
You don't change directions in the same string.
Espérame un poquito. No escucho. 2002 y nada más. Nada más. La torsión yo lo hice solamente para que tuvieran como un muestrario de torsiones. Ah, da lo mismo. Toda la cuerda tiene que estar anudada en Z o toda la cuerda en S, ¿ya? En este momento no nos importa la torsión, pero podrían ser cosas distintas. Por ejemplo, las que están anudadas en Z podría significar que estoy hablando de una mujer y la que está en S un hombre, por ejemplo. Claro, es que yo les contaba a los chiquillos, a los voluntarios que estuvimos hablando un rato antes, cuando yo hago este ejercicio en el museo, es un curso mucho más largo y termina con un proyecto. Y ellos lo que han escrito, por ejemplo, han hecho árboles genealógicos con quipus. Y, por ejemplo, le dan un color a una familia, otro color a otra familia, y los hijos de ellos son mezcla de colores. O, por ejemplo, ya mezcla de colores, pero los que están torcidos en S son mujeres y los que están en Z son hombres. O, por ejemplo, algún color distintivo a la gente que ya murió. También se puede hacer eso. Entonces, uno le va dando significado, o los que están enganchados en recto o en verso significan diferentes cosas. Entonces, ustedes le van dando como el significado. No hay un significado armado y estricto de lo que significa cada cosa, sino que uno le va dando el significado. Un resumen.
So people were asking about the sense of the torsion or the sense of the notes and so on. So here we are not worrying about that. But for example, having different colors could be like women and a male were together and then they have children. So you can use like a color for the women, then a color for the men, and then use the two colors for their children. Or it could be that somebody died that year, so you would use a specific color for indicating that. But there's like not universal code, it's like the meaning is the people is giving them the meaning as the way they were, or till now.
Claro.
Maybe there is,
Sí.
but we don't know.
Sí, hay gente también que, por ejemplo, ha descrito sus casas. Una cuerda para una casa, otra cuerda para otra, en diferentes periodos de su vida que ha vivido, y sus mascotas, la gente que estuvo acompañándolo en esas casas. Entonces van contando toda una historia con respecto a los colores y a las fechas que van anotando en las cuerdas.
So there are some quipus that, for example, test the history about somebody, so different groups of ropes and knots are going to be like the houses where he lived, and then maybe if they had pets and so on, and all of this is going like to be attached in different groups, different colors, different materials, and all put together and tell a whole story.
Y es súper importante que, bueno, esas cuerdas que ustedes tienen, ya les dije, yo las hice a mano, pero también vienen de lugares especiales. La que se siente más suave, ¿se dieron cuenta? Y se siente más suave, ¿cierto?
So did you feel that there is one of the ropes that is softer than the other ones?
Que es jaspeada, como café con beige. Esa es alpaca, ¿ya? Entonces, para que vayan desarrollando esa memoria táctil también, que al tocarla entiendan qué material es. Y esa viene de un campo en Pencahue, no sé si conocen, es como de Talca hacia el cerro. Es una señora que tiene sus alpacas, y de ahí vienen.
So
Así que,
the one that indicates the day, that's the softer one, comes from an alpaca, from alpacas that were raised by a lady that lives
en el
in
cerro.
the Talca, by the Talca zone, but that she gave the wool of the llama for building these ropes.
La naranja es de una fábrica nacional que se llama Reginela, que bueno, las fábricas textiles nacionales están cada vez como cerrando. Entonces esta es una de las últimas fábricas que hay de hilados acá en Chile. Entonces también fue elegida como especialmente para esta ocasión y es de lana de oveja. Si la tocan o se la pasan por la cara van a sentir que pica más, como se nota en la cara. Sí, es que eso tiene que ver con el grosor de la fibra. Claro.
So the other one, the orange one, is from one of the last textile fabrics that are still here because there are less and less. So this is local, and you can feel that that is thicker than the one from the llama because the fiber it's more thick. So that's why when you feel it, it's not that soft as from llama.
Y en los quipus arqueológicos, bueno, los más antiguos, antes de la llegada de los españoles, no había obviamente oveja. Entonces no se ocupaba ese material. Pero cuando ya llegó el español, se empezó a incluir la oveja y las cuerdas que eran de lana de oveja eran para hablar del español. Inteligente.
So there were no sheep before the Spaniards came. So the archaeological quipus are made from just llama wool, but then the Spanish came with the sheep. So the quipus that contain wool from sheep were used to speak about the Spanish. So like the sheep wool would mean the people that came for colonization.
Sí. Y la otra cuerda, la que tienen que es negra con mostaza, ¿la ven? La que es en espiral, esa es de algodón. ¿Ya? Entonces tienen 3 materiales distintos.
So the one that has black is from cotton, so it's really different material from the other 2.
Y yo intenté que fueran todos materiales locales, pero no encontré algodón de Chile. Y esa es de España. Entonces sería un quipu colonial. Un quipu.
It's a post-colonization.
Claro, habla
So
mucho de
Ita
nuestra historia.
Really trying to find local materials, but she couldn't find cotton that was produced here in Chile. So the cotton is imported from Spain. So that's what we are joking about. It's like a post-colonial quipu, in fact.
Sí. Habla mucho de nuestra historia, de cómo ya se han dejado de fabricar cosas aquí y al final terminamos trayendo cosas de afuera.
So keep telling things about our history because we are stopped producing these things locally and we are bringing them from abroad.
Ya. ¿Y cómo van? ¿Sí? Muy bien. Sí. En el caso del mes, yo tendría este espacio vacío, lo voy a marcar espacios. Entonces, esto, claro, así, aquí estaría la cuerda del año, ¿cierto? Las 4 zonas, y el del mes estaría ocupado solamente estas zonas de aquí, ¿cierto? Entonces, por ejemplo, yo nací en mayo, entonces sería 5. Solo eso. El que nació el 12 tendría aquí 1 y un nudo largo de 2, ¿cierto? El que nació en diciembre.
So now you're going from the chord of the year to the one of the month. So you're going to leave the thousands and the hundreds without any knot, and then depending of the month you were born, you're going just to use like the tens or only the units. But keep like in concordance with the other chord.
Se usa de forma ritual. Hay algunas comunidades en la zona andina que mantienen sus quipus y los sacan para las ceremonias, pero no se ocupa diariamente como con fines utilitarios. Pero sí, se mantienen y de hecho hay museos de eso en las comunidades y los pasean. Y hay gente que, por ejemplo, ha adaptado también el quipu ahora a otros usos, pero que se mantenga el uso del quipu como se usaba en ese tiempo, no. ¿Cómo van? De forma ritual. Los sacan a ciertas ceremonias. A veces también para llevar algunas cuentas muy básicas, pero no a este nivel. Yo les decía a los chicos también, antes de entrar a la clase, que cada cierto tiempo sale una noticia como descifraron el quipu. Y es como clickbait, y uno se mete así como ¡ah! Y sí, descifran como alguna cosita. Por ejemplo, la última vez se dieron cuenta que uno de los quipus que encontraron tenía 7 colores, 7 grupos como de colores de cuerda. Y del pueblo de donde era el quipu habían 7 familias. Entonces, como que por ahí podía andar como en ese caso, que es como, yo creo que es muy particular como a casos, claro.
So there's always in the news like, they deciphered the quipu, but in fact they are like, deciphering just small parts about quipus, and the last one that was told, it was a quipu that had 7 different colors and came from a village that were only 7 families living there. So sometimes the meanings of these quipus are very local, like are really related to where they came from, the family, the village, and so on.
Pero hay ciertas teorías también sobre los colores que tienen que ver con hacer como cruces entre los usos de los colores en otros soportes y esto. Por ejemplo, han visto que el amarillo siempre es como el oro, el blanco es la plata, el rojo tiene que ver con sangre. Entonces, dependiendo del contexto, puede ser un guerrero, podrían estar hablando de un guerrero, o podrían estar hablando como de la femineidad, el rojo de la sangre también. Entonces, hay algunas cosas así que se proponen, pero no se sabe. ¿Tienes preguntas?
So, for example, for interpreting the meanings of the colors, there are some proposals that say that, for example, yellow is related to gold, or white is related to silver, or red is related to blood. So, red could also be related to females because of the blood also. But we don't really know.
¿Cómo?
Dice que cuando terminó de hacer el año, le quedó muy cortita la cuerda del año.
Claro.
You are from the 1900s.
Te descubrimos.
Entonces pregunta si para el mes tiene que respetar las zonas que quedaron en la cuerda cortita o lo hace como relativo a eso.
No, se respeta las zonas. Puede quedarte, por ejemplo, las zonas acá y la cuerda muy larga hacia abajo, y hacia abajo nada, vacío. Respeta solo las zonas. Yo lo hago del tamaño que pienso que ustedes van a usar, porque no sé cuánto van a usar. Entonces lo hago del máximo, pero después lo que pueden hacer es cortarla y anudar para dejar parejo.
After you build the year, maybe the strength from the year is really short. So for putting the knots for the month, you have to have the same zones that you have in the shorter one, and then it doesn't matter if there's like lot of course, like a lot of rope, and then at the end you can just cut it. But the knots should respect really the zones.
Sí. Lo otro que es importante, que yo lo asumí porque siempre se lo he dicho así, como que anoten desde arriba hacia abajo, ¿ya? Que empiecen de acá al nudo, atención, que anuden primero acá arriba y después los siguientes abajo, porque si empiezan de abajo hacia arriba, se les van a ir moviendo los nudos, porque al anudar se acorta la cuerda. Entonces, de arriba hacia abajo anoten.
So you always have to build every number from the top to the bottom. So from the thousands to the units, otherwise the knots are going to be misplaced.
Y en el caso, por ejemplo, del que nació en el 2000, es muy difícil distinguir zonas. Entonces, ahí va a necesitar quizás más cuerdas para poder distinguir que existen 4 zonas. Pero nunca hay quipus de 3 cuerdas. Esto es un caso muy especial para ustedes, pero en general tienen 20 cuerdas por lo menos de ahí en adelante. ¿Ya? Claro, sí. Ocupa solo las últimas 2 zonas. Sí, estamos. Súper. ¿Les gustó? ¿Sí? Ya, qué bueno. Bueno, sigan practicándolo, enséñenlo también. Ah, sí, les tengo una misión. Les tengo una misión. Súper importante.
Pay attention because there's homework and it's not only
Sí.
about this.
Es una misión. Hay un quipu ahí afuera, en recepción. Ahora, todos deberían ser capaces de leerlo. ¿Ok? El examen, sí. Y tengo la respuesta, pero... Sí, ya. Entonces, eso. Las pistas es que las cuerdas primarias corresponden a años y las secundarias corresponden a día y mes. Ahí se las dejo.
So, you see that there's a kipu that was built, that Icha built for us in the wall, like in the white wall. So, for tomorrow, you have to tell us which years are coded in that kipu, and the only hint that we have is like the primary chords are going to be for the year, and then the other chords are left for month and day.
Es un quipu temático, así que tienen que adivinar también la temática.
It's a thematic kipu, so maybe there's just numbers, but these numbers mean something. So you have to also guess what these numbers mean.
Sí. Y sin soplar los voluntarios, porque saben.
And the volunteers, keep your mouth shut.
Sí. Muchas gracias por participar, gracias por invitarme, por poner atención.
So now we have the welcome party reception over there. So please go outside and thank you very much. And we thank Icha again for this beautiful.
Gracias. ¿Cómo te fue? A ver. Sí, súper. Claro, tienes que ver que te queden como más alineados, ojalá.
Sí.
Como para que se entienda más, pero sí, está bien. Sí.
Hello,
hello.
Claro, es que también
Before you
como yo
leave,
pienso en
guys,
mi hijo,
guys.
claro, estaba aprendiendo a escribir.
Hey. Remember that today we started at 8:30, but tomorrow we are starting at 9 sharp, okay? Because then otherwise the program will shift.
Yo pienso en mi
Yeah,
hijo,
please
cuando le
be
estaba
on
enseñando a
time.
escribir,
Remember,
es como
there is a
exigirle
long
que
way to
escribiera
come.
bien desde un principio,
Swiss
pero
time.
no tiene sentido.
Thanks.
Sí. 1000.